right, we got some good coverage. That was a good list. All right, we are, when you do end up talking to each other, please make sure you're doing so out in the hallway. We are going to start with our first speakers here. We are going to start with Lucas Wirt. Please correct me if I'm mispronouncing anything. Lucas worked on Rust Analyzer since 2020. He has been leading the Rust Analyzer team since 2022 and is now a Rust engineer at Zed. He also co-authored the Ferosine language specification. Also with us is Vlad Biskrovny, who currently works at JetBrains. Vlad started working there in 2017 on the JetBrains Rust plugin team and helped turn that into Rust Rover. So my question for you guys, is this a battle of the editors? Is this a happy collaboration?
We hope so.
The answer is yes, it seems. All right.
We'll try to figure it out.
Wonderful. Well, we're super excited for your talk, and we'll turn the time over to you guys.
1, 2, 3. So, my name is Vlad. My last name, I'm sure you will never remember it, so I translated it to English. It's directly translated as Bloodless, so you can remember me as Bloodless. Yeah, I work at JetBrains for 9 years already. So, what we're going to talk today. What's an IDE? Well, you know, it's this black, text editor where people write code usually. An IDE is not just text editor, it actually integrates a lot of things like file explorer, terminal, debugger, like basically everything that a developer can need to write the code. But the most notable part of an IDE, I believe, is what we call a smart editor. It's not simple text editor, it's a thing that can provide completion, navigation. It's something that deeply understands the code. And in the scope of this talk, we explain what's behind it, like what powers all these smart features of the editor. And actually, modern Rust editors are powered by basically two different analysis engines. It's either Rust Analyzer, which provides LSP for a wide range of editors, and Rust Rover. And the thing is that Rust Rover does not use Rust Analyzer. It provides its own code analysis engine. So in the scope of this talk, we're going to discuss how code analysis is implemented in Rust Rover and Rust Analyzer, and how is it different from the compiler. And speaking about compilers, actually to provide such smart features in editor, an IDE should basically do the same as the compiler. Very similar things, like compiler should parse the code, and Rust Analyzer also parses the code, Rust Rover also parses the code. Compiler perform name resolution, IDEs perform name resolution, type inference, MIR, everything basically. So why we can't just reuse the compiler then? And I think besides historical reasons, it's mostly the main thing is an optimization focus. Compilers are optimized to compile as much, millions of lines of code per second. It's basically throughput. For IDEs, throughput is not that important. The much more important thing is latency. That means responsiveness. So like I typed a dot and I want to see completion as soon as possible. At this point, I don't care about other functions in this file or other files or errors, anything. I just want my completion instantly. And the thing is that to provide the thing is that this optimization focus shapes the compiler or IDE architecture significantly, like algorithms chosen and stuff like that. The compiler is typically implemented as such a pipeline, like it first parses everything, then produces AST, then it turns into some another intermediate representation. Like name resolution happens for everything. Macro expansion happens everywhere. Then type check happens for each function, and so on. So there are this stage of compilation where everything is batched. IDEs usually a classic IDE kind of work in the opposite direction. Like I need completion at this particular point, and then I want, certain names to be resolved in order to provide this completion. And it kind of works lazily from the point where analysis is needed. We even highlight, we try to even highlight only what you see on the screen, even not the entire file at first. So yeah, move on.
Yeah, so going into that a bit more, so a compiler usually has this phase approach, whereas an IDE doesn't have distinct steps or phases in what it does, right? So a usual compilation pipeline is something like, you invoke the compiler, it does semantic analysis, it does code generation, then it delegates to the linker to actually link the final binary, and then the entire process exits. Whereas IDEs are more a long-running process, so you start them up, they load the workspace, and then they just iteratively change the view of the world depending on what the user does, like edits and the like, right? So we don't have this phase separation that neatly, because we only do things lazily and try to only touch the things that we are interested in. And that obviously, as was already said, has implications for the architecture. And one big part of that, for example, is resource consumption. A compiler tends to use a lot of arena allocations, for example, because you have distinct phases where you don't need all of this information at this point anymore. So you can just allocate this kind of stuff like symbols or type information or whatever in an arena and discard the entire arena allocation at the end of the phase. We can't really do this kind of stuff in IDEs because we kind of need everything at any given time if it becomes relevant again. And so we usually have to think more about memory reclamation, garbage collection in that kind of regard, which obviously Rust Rover and Rust Analyzer solve in different ways by nature of, well, the language they are already implemented in. We'll go into a bit more detail in the later architecture section. Right. To highlight a bit abrupt change, but to highlight one of the bigger design differences, for example, as well, is in terms of the syntax tree representation between the compiler and the IDE. So the folks that know programming languages and implementations a bit, obviously, I would assume they know what an abstract syntax tree is. So basically, the source code parsed into some kind of tree structure, so you actually know the structure of the program. And there's two kinds of variants commonly known, which one is the abstract syntax tree, which cares about all the important bits of the tree. So kind of every single token that is not white space, that is not comments, that have kind of meaning to the program. And then you have the concept called the concrete syntax tree usually, which also retains this kind of white space and comment information. The former is usually used by compilers because they don't really need the white space or the comments. They don't, again, have any meaning for the program. Whereas IDEs tend to retain this information by nature of them trying to do refactorings and the like. So they want to transform code and want to retain white space if necessary, retain comments and the like. And so the left side here, for example, is how Rust C would kind of represent the syntax tree. Right side is more of what an IDE would use. It would retain the so-called trivia tokens. And in a similar vein, when it comes to macro expansions, the IDEs also handle it a bit differently. When Rust does a macro expansion, it kind of treats it like inlining the expanded macro syntax tree into the place where it was invoked. So you end up with this one fully expanded tree. The IDEs don't really do that because they want to still work with the original tree to know what the user is actually doing in the source. And so it tends to keep macro expansions as kind of like the separate trees. And whenever it wants to do something within a macro expansion, it goes from the one syntax tree from the macro expansion invocation to like another tree. So we have kind of a tree of trees in that regard. Yeah. With that said, let's talk a bit about timelines.
Yeah, a bit of history. So the whole IDE story looks like the Rust IDE story. I mean, looks like that. So Rust Rover, I mean, its predecessor as Intellij-Rust plugin was actually the first. Then was RLS. I'll talk a bit more about it, and then Rust Analyzer appeared. Regarding RLS, it's a very interesting story. If you kind of think that, okay, maybe IDEs are not so different, let's still try to reuse compiler as analysis engine for editors. This approach was actually tried out. The RLS, it stands for Rust Language Server, was a brave attempt to turn the Rust compiler Rust-C into an IDE, basically, IDE backend. And it worked via such so-called safe analysis. So basically, Rust-C compiler was invoked, and it saved the huge JSON files to disk, describing like everything about your project, like how stuff is resolved, which types are there where, and stuff like that. And then LSP, some LSP server could read the safe analysis and provide intelligence for text editor. So, well, yeah, this approach failed. It suffered from high latencies. It was basically very, very slow. It was impossible to provide completion, sane completion, let's say good completion. This way, actually, RLS even didn't use Rust-C for completion. It used a separate tool called Tracer, which was like, I don't know, regular exploration-based completion engine. And also, it was fairly difficult to implement any code modification features in such a IDE backend, like, assists, quick fixes, stuff like that. But yeah, actually, Rust Rover predecessor, Intellij-Rust plugin, was started earlier than RLS. It was started by Alex Kladov and Alex Kudinkin in 2015, when they were JetBrains employees back then. And that was a classic IntelliJ platform, IntelliJ plugin. JetBrains has so-called IntelliJ platform, and basically each JetBrains IDE is a platform plus some set of plugins. So we had this Rust plugin back then. IntelliJ platform provides API for Java or Kotlin, so basically all plugins are written in some of these languages. I joined this project in 2017 as an intern, and I started working on type inference back then on macro expansion, then on name resolution. Basically, I wrote a significant part of this plugin since then. Yeah. Next slide, probably.
Yeah, so a bit of time on Rust Analyzer. As you can tell, the first line didn't change much. It was also started by Alex Kladov.
Yeah, the same person basically left JetBrains and started Rust Analyzer,
So technically, it started out as another approach for parsing Rust. Like they were playing with the idea of, okay, how can we make a nicer Rust parser that is more generally useful for not just the compiler but the IDE.
I think his first idea was to bring this parser into the Rust compiler.
Exactly.
To fix RLS, basically.
It was meant to replace the initially to replace the parser and the compiler. It didn't turn out that way in the end, but it did turn out to become Rust Analyzer. In fact, at some point they put on top just a very simple LSP message loop effectively, and then it just started growing from there. Obviously, it's written fully in Rust, and through contributor contributions, it gained type inference a year later, basic macro expansion a year later, and as it turns out, 3 years after that, it actually got moved into the Rust project as a part of the Rust project. So it is now official. It is now the official language server, basically fully replacing the Rust language server and having sunset it effectively. With that said, so let's talk a bit about some of the fundamental language features that the language has that makes it a bit annoying at times for IDEs, or that are just kind of tricky, really, in general. With the most basic one being name resolution. At the heart of Rust, really, as you know, like the kind of the units of compilation, like the one thing in Rust is a crate, and a crate is made out of modules, right? And the module graph is kind of necessary to do basically any semantic work in Rust. And so this is a big requirement for us to do compilations, to do highlighting and the like. And so before we can do anything, we always have to resolve the module graph. Turns out it's not that simple, unfortunately, because in Rust, the module graph is cyclic. It allows cycles by referencing cycles like these imports here. So let's go through this example. So you can see we have two modules, foo and bar. They have a bunch of re-exports in them. And so let's try just tracing back this function call in the main function to see where we have to jump to actually get to the final definition and things. So we have this bar colon blue call, which means we look for an item called blue in the module bar, which will lead us to this glob re-export, because this will, in the end, have a symbol with blue in it. That means we now have to look at all the modules all the symbols in the foo module, which leads us to this re-export, which is just a very weird rename. So now we're actually looking for the symbol called red, which comes from this glob import, and so we have to jump back. And now we have found the final definition. As you can see, this is kind of chaotic, and clearly not a clear path to the actual symbol name. And this is what kind of forces the name resolution algorithm in the language to actually be a fixed point iteration. That means we basically collect all the module items of the root crate module, including all the child modules, and then we collect them those as well. And we have collected everything we can see. Then we try to resolve all the imports in these modules as much as we can with the information we have right now. Then we do macro expansion for all the macros we have resolved so far. And then we just do the same again. We recollect everything from these macro expansions. We try all the unresolved imports and so on. Do that until we find we have no more work left. And if we resolved everything, we have successfully done name resolution. If something's unresolved, we are out. That is effectively how name resolution works in Rust on paper. It's technically quite simple, but the language has quite a lot of features that make it a bit more complicated, actually. We have namespaces, for example, right? Type namespace, macro namespace, value namespace. We have visibility modifiers. We have public exports, public uses, pub crate. And we have fun things like this path macro that you can put on modules. So thanks to macros, we can't even assume that all the source files for a given crate live inside some subdirectory where the root module is. Because you have the path macro, which can point to anywhere on the file system. You have the include macro, which can do the same. You have proc macros, which can also do the same. This alone makes it kind of annoying for us already to be able to tell what source file, what source files belong to which crates without actually having built the entire module graph. So this kind of goes against what we want to do, which is we want to be as lazy as possible. For this step in Rust, we have to be basically eager in all kinds of ways. And it actually gets worse. This is valid Rust. You can declare a module inside a const parameter default. I would hope no one will ever do this because it's really not useful in my opinion. But this is valid Rust. This is not supported by IDEs usually because this would force us to do way too much work, so we just do not allow this. But yeah, this is the kind of stuff we sometimes have to deal with here, which is not great. Which leads me to another interesting way of how things work. So as some of you know, macro rules have weird item scoping behavior. They don't behave like normal items. They have a textual scope. So they are only in scope after they are declared, instead of inside the entire scope they are declared within. And so there is an interesting error that I want to show here. So we have this macro, which basically emits another macro with the same name that doesn't do anything. So when you invoke it once, you just redeclare a macro. But what happens if we now invoke it again? Which one do we invoke? And it turns out the compiler actually rejects this for a good reason. Well, the node is a bit weird in my opinion. It says can't, it's ambiguous because of a conflict between a macro expanded and a less macro expanded name. What? Kind of weird phrasing, but I guess it's difficult to like phrase it better. But the reason why it actually refuses to do this is allowing this to resolve in one way could leak the fixed point iteration resolution. Because depending on which one of these you invoke, you expand first, you will get a different final resolution. If you expand line 7 first, the next one should, in theory, expand the inner macro. But if you expand line 8 first, we would expand the outer macro twice. And so this is just a safeguard to prevent this fixed point algorithm from actually leaking its resolution order. And there's a bunch of like minor details like this, which with macros brings me to the next topic. Folks that know me know that I really dislike macros, simply because they make IDEs kind of a nightmare, in my opinion.
Me too. Who likes macros? Anyone?
And so declarative macros are kind of fine because they behave predictable. They are completely built into the language. The bigger issue really are procedural macros because they can define very interesting domain-specific languages, and we still want things to work, like hovering, for example, should yield decent results, right? Which kind of works these days if the macro is cooperative enough with how it uses spans. But the issue is that proc macros are, in the end, user code that just runs. They are just dynamic linked libraries that the compiler or the IDE in this case loads. And on paper, they are just tokens in, tokens out. They just do a transformation on the tokens, right? But because they are actually just user code that is running on the machine, it's not just tokens in, tokens out. It's side effects in, side effects out. Because they can read files, they can write files, they can read process environment, and so on. And this kind of means that, in theory, caching proc macros breaks them if they do that, which is why I believe the compiler today doesn't do it. The IDEs still do it because they want the performance gains from it. So that's why some macros may behave weirdly if they are run in the IDE and look stale. But that's something that we are fine with paying. But the other big issue is, since they are user code, that run in the host process, they can actually hang, they can crash, they can call process abort and just take down the compiler. They can even fork if they want to, which has interesting behaviors on some systems. And obviously, we don't want the IDE to just go down with that, right? So what we actually do is we have a separate process that loads and runs proc macros that we then talk to via JSON RPC, like a custom remote procedure call protocol. Simply to prevent us from, if the proc macro crashes or whatever, it takes down the server, sure, but then at worst we lose some of the proc macro state, and we can just spin up a new one and continue. So this is just a safeguard against it. And then we just spawn a couple ones because of concurrency concerns. Yeah.
Interesting part is that this pros macro server, which is now a part of your toolchain, it's always installed together with Rust-C. It was originally implemented on my internship in 2018, but my intern, Roman Golyshev, and it was placed on GitHub, and then eventually become a part of a toolchain. So what else we have in Rust? Well, you probably heard that type system in Rust is one of the most sophisticated type system across industrially used programming languages. Well, for example, here I first define vector without specifying its containing type, and the type is inferred later, just when first push comes into this vector. But the good thing about type inference in Rust is that it's well scoped. Other function bodies don't influence type inference. Can't influence type. Well, let's say in most cases, absolute most cases can't influence type inference. In the other places, let's not speak about RP today. So we can infer types in main without looking in other function bodies, looking on just their signatures. But well, still in Rust, the type inference is so much complicated and has many, I don't know, thousands on very arbitrary rules. I don't know. Like look at this example, for example. There is a rule in Rust type inference that you can't resolve a method on a variable which type is not known. And I don't know, it's not just a rule, it's just how name resolution works. Like you fairly can't resolve a method if you don't know the type of the receiver, right? And so this code does not compile because you don't know. Wait, I didn't switch the slide. I forgot switching the slides. Come on. So yeah, look at this example here. We have a lambda, and it walks on its on its argument. It does work because at the point where lambda is defined, we don't know the type of the receiver. We can't resolve its method. But let's look at this example. Basically, it's the same. We first declare lambda. It's passed as first argument to function apply, which calls it for the second argument of the function apply. What do you think? Does it compile or not? Okay. Who think it compiles? Fine. Who think it's not? Okay. Okay, it works. It works, but why? Why does it work? Actually, because in the Rust compiler there is such I don't know order of inferent types in a function call. So it just first type checks.
5 minutes. Speed up.
It just first checks everything, but not lambdas. And at this point, I decided, okay, what if I wrap this lambda into, in this case, a tuple? Do you think it works now? Who think it works? No one. Perfect. Well, yeah, it doesn't work because it's not lambda anymore. So there is a compilation error. And type inference, like it's full of such arbitrary rules and fairly difficult to re-implement all of them. Another example, why we have MIR in IDEs. I hope you can see this example. Well, just because in order to resolve on line 12 the method foo, you have to calculate the value of this function. And to evaluate its value, we need to basically build. We need to basically have an interpreter just inside an IDE and compute its value. Okay, let's move on to the architecture. I tried very, very hard to simplify the architecture for Rust as much as possible. So you see the totally simplified chart. Almost nothing is here. Like, yeah, very simple. We'll try to understand it right now. So the first thing happens when you open any project in Rust Rover. It's a project model. So we invoke cargo metadata. It returns us a huge JSON describing project structure in terms of cargo packages and dependencies between them. We also immediately call cargo build with flag compile time depth, which builds prods macro libraries and invoke build script for us. And also we call a lot of different stuff actually, like Rust version, to make decision about the version. But the main part here is cargo metadata, which returns this crate dependency graph. And once we know crate dependency graph, we know basically directories with Rust files we can work with then. Okay, let's now figure out how IDE sees Rust files. And we use an abstraction over syntax trees called PSI, which stands for Program Structure Interface, but it doesn't matter how it's called, basically. It's a set of Kotlin interfaces, one of each per each kind of syntax node. You can see such an interface definition on the left side. And on the right side, you can see how an actual PSI tree for Rust file looks like. An important thing is that PSI is directly mapped to text because everything stays there, like keywords, comments, white space, just like Lucas explained previously. And thanks to that, we can manipulate PSI directly, and text in the editor immediately reflects the changes. All cool IDE features basically works on the syntax tree, like refactoring, I don't know, all code modification features, quick fixes, stuff like that. It does not modify text directly. And another important point is that PSI is not only a syntax tree, this abstraction is backed by two different data structures. The problem with syntax tree is that it consumes a very huge amount of memory, and it's very inefficient to hold it to every Rust file in your project. It's most useful for only for the file that is currently open in the editor. So for other files, we usually compute so-called stub, which is very simplified ST. It's very similar to compiler ST, but it's even more simplified. It doesn't contain function bodies, for example, because in Rust you don't need function bodies in other files in order to provide intelligent features in other files. Yeah. And cool thing about the stubs that in PSI that syntax tree can be computed lazily. So by default it's stub, but once you call get function body, the Rust file is parsed lazily, and we have its syntax tree under the same PSI interface. Okay, I can speak about PSI for hours, so let's move on. Indexing. Yeah, you probably know this whenever you open any project in any JetBrains IDE, you see this index in progress. We recently renamed it to Analyzing project, by the way. So what's indexing? That's basically map-reduce index, where each file we already know from project model, each Rust file is parsed and in parallel and mapped to a set of key-value pairs, which then joined into key-value database. Key features of the index is that each file is processed in parallel. It's stored on disk, so it outlives IDE restarts, and it's really fine-grained incremental. So the index is updated whenever you change. Whenever you change any file, only this part of the index is incrementally updated. We have many indexes, like trigram index for find usages and basically any text search optimization. Symbol index for go to function, go to type. The most important thing is that we have so-called stub index. I hope you remembered from one of the previous slides that PSI can be backed by stubs, and stubs are built during this indexing. They are serialized and stored on disk. So whenever we want to obtain PSI for some Rust file, we basically load a stub from index from disk, and it works almost instantly. interesting that during indexing we don't even parse Rust function bodies. We just skip them, like by counting braces on just Lext tokens. So indexing works. Indexing is heavily optimized, by the way. And at this point, I'm gonna ask you, what's the most important thing on this diagram? It's actually this dotted line. Remember at the beginning of the talk, I was telling you how it's important for an IDE to do things lazily, to deliver low latencies, and that the main difference to compilers is this kind of optimization target. And now I'm telling you, like, well, you know, we're actually taking all Rust files and parse them in parallel. It kind of makes sense, right? And the thing is that maybe in the ideal world we could do everything through the lazily, but it seems not possible to deliver decent latency even in languages that are not fairly simple than Rust without some eager phase. And the true art of the IDE design is to drop this line in a proper place. The eager phase is this eager phase is inevitable, but it shouldn't be incremental, and it should be incremental in a highly fine-grained way, so that you know you can change so that you can't change one declaration and it validates everything, right? And the thing is that for most programming languages, MapReduce index is enough in the eager phase. Let me quickly show how it works in Java. In Java, every Java file has package declaration. So we can index one Java file without looking on other files, and by just string concatenation with the package declaration and any name in this file. And then whenever you want to resolve something else, you just like look up import statement in the same file and look up this key in the index, and that's it. Everything can now be done in a lazy manner once you have index. But you know, Rust is not Java. It has so perfect name resolution. It doesn't have package declaration, and even if we had one, we don't know which index key to look up there anyway because of this recursive manner. So yeah, we had to bring this name resolution into eager phase. Okay, let's skip this part now.
So we're running a bit low on time, so I'm just going to quickly show basically the one slide that is kind of different to the architecture that Vlad showed, which is instead of having a bunch of indices, Rust has a query-based compiler, like the Rust compiler. And so instead of doing all this MapReduce stuff, we just have a lot of queries that know the dependencies and thus can tell when they need to recompute. Which means, in this case, we have this definition map query. It's an early name resolution, which depends on the item tree query, on the parse query. And so if the parse query gets invalidated, but for example, the item tree query does not, we know that we do not have to recompute the name resolution because we know that our dependencies have not directly changed. This is what the compiler also pretty much does, just in a different kind of flavor. And it means it's very easy to just write fairly incremental compilation setups, as long as you take care not to draw dependency edges that actively hurt it. So in this case, if the definition map was depending on the parse query, and you do any kind of edit, we would now have to recompute everything because it would always invalidate the outermost query. That's kind of the gist of this kind of difference to the approaches here. And then on paper, it's basically just we have a function, we put an attribute on it that does all the plumbing for us for dependency tracking, for memorization. The most important bit, obviously, to be able to reuse already computed results if they have not changed. And then it also does a bit of garbage collection for us via least recently used caching. Yeah, I don't know. We are out of time, I think, right? Or yeah, then we can draw a cut here. I think this is not too interesting because project model is what Vlad already described. This is exactly the same they are doing. So yeah, I think we can cut here.
All right, everybody, let's give Lucas and Vlad a big hand. Thank you. We will be handling questions outside here because we need to give time for our next speakers. Just a couple of housekeeping things. I'm not mad, but I am disappointed. We did have a few people come through some of the doors during the talk. Please make sure that we are offering our speakers a courtesy of not having a loud metal chunk that I'm sure a few of you heard while we were out. Also, we have lots of cushy seats for those of y'all sitting on the stairs. That does obstruct people being able to get in and out. So please come and sit on a seat for the next talk, okay? Thank you very much. We will break until the next talk.
Hey, it wasn't fair. Like, I mean,
Huh?
we spent a lot of time on just setting up the stuff.
Yeah, we messed up the timing, to be
What
honest.
the?
Huh?
We had plenty of time initially.
We did not. Yeah, initially, but
Initially,
kind of. Yeah.
Yeah, sorry. Yeah, it was a bit
All good.
I think garbage collection stuff was the most
yes.
important, and we skipped
sorry.
that. Okay.
You guys did great with the time that you had.
Eh.
We were yapping too much at the start.
We spent too much time to set up stuff initially.
Right.
We definitely put the focus wrong. We should have cut down the start more.
Yeah.
By the way, it happens.
I was interested. I
Yeah, it wasn't bad, I think. But
Who can help
we
me
didn't
with this
talk
stuff?
about the part that we
Right.
wanted to talk about the most. That was the issue, right?
Oh, that's always the risk of backloading the most interesting parts, I guess.
Yeah, but like you want to do like a proper introduction to like topics, you know?
Right, it's so hard.
You just gotta write a blog post and ship a video.
Yeah, that's what I always tell myself. Writing a blog post out of the talk, and I'm not doing it.
Yeah. Right.
So who can help me with this stuff?
What help did you need?
Okay.
Oh, getting
Yeah,
getting
get
on
rid
here?
of it.
I think we need to get you in line here because our room tech is right over there, the bearded fellow currently helping Fulbert.
I wrote a pronunciation guide, right?
Yeah. I'm just making sure. That's fine. You know, I don't want to read it. If you
Yeah, lots along the slides.
Yeah, you know, it's like as far as names go, it's sort of reasonable still, but
Yeah, the tech people are supposed
it's
as MC, if I read it and I go, I think it's this, and then I don't check.
oh yeah,
then I
no,
get it wrong,
you just
and
need to
then I
do it
feel
with full confidence, and you'll be good.
Anyway, quick. Didn't do this for the first talk. We're gonna do it for this talk.
Okay,
Timing.
right,
I'm gonna sit in the corner there.
right.
If you want to sit me somewhere else to make it
That's
less
fine.
obvious, it's fine. But like, I could also sit in the middle.
I'll notice.
Anyway,
Or not,
The
it's
talk's gonna
fine.
be 20 minutes.
What?
The
No,
talk's gonna be 20 minutes, right?
it's going to be 30.
30. Okay, 5 minutes questions then.
Yeah,
30 minutes talk.
Yeah.
5 minutes questions.
right.
Okay.
I mean, roughly. Okay, so I timed this at 31 minutes. So, but that's going to be fine.
I'll round it to 30, and I'm gonna.
Well, I mean, but don't be worried. Like, I'm not going to ramble on for 45. Like, it's close. It just might not hit 30 minutes exactly.
45 minutes. I'm gonna give a note on 10 minutes, 5 minutes, and then just like
It's fine.
2 and 1 maybe.
I didn't think it mattered. Yeah, I mean, whatever.
In the corner, and I'll make sure that you'll keep time.
Cool. These are clean glasses? Yep.
I don't think they took steps.
All right, welcome back, everybody. We're going to get started real quick here. This is Volker de Vries, a systems programmer at Trifecta Tech Foundation and Tweed Golf. Maintains zlibRS and bzip2RS, as well as co-maintainer of Rust-Lang Standard Arch, which is a bunch of SIMD intrinsics and things like that, and is a contributor to Rust-C, as you might imagine, and LLVM.
All right. Welcome to Stabilizing Decade-Old Features. The thing you need is unstable, and that sucks. So this talk is about stabilizing features, but it's perhaps more about becoming the kind of person that is able to do this kind of work, which had long been an ambition of mine, but it's not as if there's like a step-by-step guide that you can follow. But I've been at it for about 2 years now, and I think I've worked on some cool stuff. And so nevertheless, I hope that even if it's not your ambition to become like a regular Rust contributor, it's still interesting to learn something about how the sausage gets made. So if you've been using Rust, you've used unstable features, or you've seen unstable features, right? You're browsing the docs, your eyes land on the perfect solution to the problem at hand, but even though the compiler knows perfectly well what you mean when you try to use this function, it actually won't let you. Someone decided that it isn't ready yet. And that can be quite frustrating. Now, I do think that overall, this is a very good system, right? Because it allows normal users to play around with experimental features. You need to enable the nightly toolchain, enable the feature, and then you're off to the races. And really what you get is a very normal Rust experience where cargo works, Rust Analyzer works. It's actually remarkably stable for something supposedly full of unstable features. Nevertheless, the question that always pops into my mind whenever I encounter one of these errors is, stable when? When can I use this feature? When is it available unstable? And so you might click the link that is in these messages. And this link takes you to the tracking issue for this feature. And this tracks the progress of this feature towards stabilization. And so what you find here exactly has actually changed a little bit over time. So for a lot of older features, you will find many comments, hundreds of comments, discussing the design of the feature. And then we sort of realized, like, well, GitHub comments aren't a great way to have a conversation on the internet. And so now most of that discussion happens over on Zulip. But that means that for a lot of modern tracking issues, there isn't actually all that much there. Kind of either way, it's really hard, certainly as an outsider, but even as someone more sort of tapped into the project, to figure out, it's like, what is actually blocking this feature from becoming stable? How far along is it? Now, something that is especially frustrating, at least to me, is if I keep coming back to features that have sort of been out before and are still unstable. Or whenever you hit one of these like issues that has sort of been open since forever. Because if you follow features like that, if you keep running into them, it can seem as if Rust development is really slow, right? It might even be, in some cases, at a complete standstill. And that is weird because actually if you go over to the repo, and this is the merge queue that we use, Borse, Rust development is very fast, right? There are dozens of PRs that are merged every day. And Rust has a release every 6 weeks.
Testing, testing. We just noticed a bunch of stragglers coming in, so we're gonna wait just a second here. All right, just as a gentle reminder, the doors are closed. That means you're stuck. Unless you absolutely have to, please don't go out the doors. We want to give Boxy as many opportunities to share what she wants and not just you be distracted by slamming doors. So, welcome back, everybody, after the break. How was lunch for everyone? It was very gezellig, I think. I would like, before we get to our speaker, to give a shout out to our diamond sponsor, Amazon Web Services. Thank you for helping make Rust Week happen. Also, we have a coffee sponsor, which is not a tier. It's just, you know, they helped us out with the coffee from Comper. So thank you very much for the coffee. Definitely needed it. That one got applause. Oh. Now, I hope you can match that same energy for our next speaker, Boxy. Thank you. Exactly what we need. Yes, Boxy's pronouns are she, her. She is a member of Rust's types and release teams. She's also co-lead of the Rust's compiler team and the Const Generics project group. There's a lot of love here. She also co-created the Unfair Rust quiz, which you should all try because, you know, it's not a typical work week unless you crush your soul a little bit. What is the URL?
Yeah, no, what the hell?
Do you know off the top of your head?
Yes. Wait, I can't. It's missing so many letters in the URL. It's hard to pronounce it out loud. This.quiz.is. And then it's fucking without any of the vowels, and then gay.
If you really want to try it, let's go get it written down, and we can come up to Boxy and get that reference from her in a bit, maybe a QR code. But I will take no more of your time. Let's hand it over to Boxy.
Oh dear. Okay. Cool. So, I've sort of noticed when I talk to people about compilers and stuff that they often act like they're much scarier than a typical software project, or not something that they can just like pick up and learn or go do. And this was very much not my experience getting into compilers. And as someone who now I think has a pretty good understanding of how compilers work, it's not something that I think is true for most people either. Next slide. So I started learning Rust and the start of 2020, and at that point I had previously only used C# as a language, and I'd not done any kind of open source stuff before. It was then late 2020 was when I did my first open source contributions to the Bevy game engine, and then maybe like half a year later at the start of 2021 was when I got involved in the Rust compiler. So at that point I did not have a very good understanding of like the language itself. I hadn't been doing it for very long, and I also wasn't that familiar with open source, but I was doing it anyway. So I kind of wanted to go through an example of what fixing a relatively small bug in the compiler might look like, and show that it's not that dissimilar from what you might be doing in any of your own projects. So this is a relatively small example. It uses an unstable feature, which I don't think actually needs to be on this code example. That's cool. So we got this bug report. This code was crashing the compiler, which is not good, and we generally try to avoid that. Cool. So this was the ICE message we got. This is fairly common. You pretty much always see these kind of messages. They're very jargon and scary. Pretty much what it's saying is that we have the trait foo, It has some generic parameters on it, in this case the self-type and the const generic parameter n. And we can see in the generics equals bit that that's the generics we have, and we have the arguments to it, which are empty, which is unfortunate and causing the crash. Another thing you see when the compiler crashes is you have a query stack trace. This kind of gives you a high-level overview of like what the quote-unquote important functions are in the crash. It's kind of like a normal backtrace, but it doesn't give you everything. In this case, there's a lot of stuff about checking DIN compatibility or object safety if you've been using Rust for more than a couple years. So we have some idea that whatever's going wrong is something to do with checking DIN compatibility. We also have the actual backtrace, which gives you all of the scary little, this is the actual functions being run on the compiler, these are the actual lines of code. And we can see similarly, we have a bunch of stuff about DIN compatibility in here. I sort of cut some lines from this that were just boring stuff like internal panic machinery that you get in any backtrace that wasn't useful here. And I cut some of the source locations that also were just taking up space. But this is roughly the kind of thing you'll see. So the first thing we should do is talk about DIN compatibility. This is only some traits can be turned into trait objects, and we call it DIN compatible when they can and DIN incompatible if they can't. The rules are somewhat nuanced, but the general high-level idea is that if you use the self-type in a trait in some ways, then we don't let you do trait objects because it causes problems, TM. Understanding the exact nuances of why we enforce those rules isn't too important for fixing the bug. All we really need to know is that we don't like it when you use self in a trait and then turn it into a trait object. There's some cases where we do allow it, and this is particularly if you use an associated type of the self-type and the trait is from a super trait of the trait, then it's fine. But we'll go through some examples of that. So here's an example where we're just using self on its own, and we get a compiler error. We have the trait on the associated type, partial equal for self, and using self like this is something the compiler is not happy about, and that's good. We have another more scary looking example. I tried very hard to get a code example which was not quite so scary looking, but it was surprisingly hard to get something that was quite small. Here we have an associated type instead of just using self, and inside of the associated type we're using the self type. And this is also a case where we're not happy about it, even though it's in an associated type, and we can get stuff not allowed. This is an example where we actually do compile this and we do let it work. We use partial equal and we use an associated type, the item on the into-iterator trait. But because into-iterator is a super trait, the compiler lets this work. This is because when you do the trait object, you have to specify the item. I guess this code actually wouldn't compile because I half-assed my function implementation and omitted a bunch of stuff, but it doesn't fail to compile due to DIN compatibility. It's because I did an incomplete example. Oh, I skipped a slide. So looking back at our backtrace, this is the place where it points us to. I've very helpfully annotated the line of code that says we're crashing here. If you are actually working on the compiler, only sometimes will there be a fix me on the line of code saying this probably crashes. This is quite involved, confusing. I wouldn't expect really anything in here to make sense at first glance to people here, but that's okay. We can go through it line by line, bit by bit, and sort of think about things. So first, we're in trait implementation. Type visitor is scary jargon. It's not too important. We can probably figure it out from context, and if you're actually working on the compiler, there'll be people who you can talk to, and they'll sit down and explain things. There'll be documentation you can read. I'm not going to do that for this talk because I don't know how long this talk is going to go on for, so I don't want to spend the time on it. We're implementing it for something called illegal self-type visitor. From our understanding of DIN compatibility rules, we know there's a bunch of rules about self-types. So this looks like somewhat expected. We're looking for self-types. We have two methods. We're handling types and we're handling consts. Still kind of unclear what the visit thing is about, but there's types and consts, and we're probably doing something about self-types in them. We'll look at types first. This is fairly standard-ish Rust code. We've got a normal match, we have a type, and we want to know what kind of type we're working with. And there are lots of kinds of types in Rust. There's like function item types, there's your normal built-in integers, there's generic parameters, there's type aliases, all sorts of things. If we did an exhaustive match here, it would be really big, so we didn't. In this case, we match on the param, and we check if it's a self parameter. Yeah. We have this control flow break and control flow continue thing, which somewhat unclear what's going on there, but from context and what we know about incompatibility rules and the name of the type we're implementing the trait for, we can probably assume that control flow break in this context means, oh, we found a self-type that we're not happy with, things have gone wrong, and we can probably assume that if we've control flow continued, everything's fine. We're also handling type aliases, especially. This also kind of makes sense. We know the rules for incompatibility involve some special casing about associated types, so that's presumably where we're doing that. So we can look more at that match arm. Allow self-projections, and all of this projection terminology is quite scary and not something we do in a user-facing way. There will again be documentation and people you can talk to about these kind of weird bits of terminology, but I'll just tell you now that projection means associated type in the parlance of scary compiler people. The allow self-projection stuff, who knows what's going on with that, but we can see this nice line of code is super trait of current trait, which kind of makes sense to see here because we're thinking about the rules for incompatibility. We know that we care whether stuff is from the super trait or not. So yeah, this is kind of vaguely what we expected to see, ideally, maybe. If you didn't expect to see this, or you didn't have a good understanding of incompatibility before this is a great way to kind of figure out the rules of the language by reading the compiler's code. It's still mostly just normal Rust code. We're matching on things, we're calling normal functions and whatnot. So if you didn't know there was special casing about super traits, you might be reading this code, you might see stuff about super traits, and you're like, oh, that's interesting. And then you can go play around in the playground and see what the behavior of the compiler is and help you figure that stuff out. So we can go through some examples. We have our matching on type aliases, and we can go back to our original example. The type alias in this context is the big associated type that's scary looking and I couldn't get smaller. We have this trait ref thing that we're passing as an argument to the function. Trait ref is more jargon. There'll be documentation. There'll be people you can talk to. It just means the part of the associated type, which is the trait and the self-type, not the actual thing we're looking at on the trait. And then we have the actual function call, where we're checking to see if the trait ref is also in the super traits. So in this context, we'd be looking to see if the trait foo has an into-iterator super trait, and ideally the self-type would be a vec of box of self, but that's not possible because super traits on traits are always the self-type implements thing. So in this case, it is not a super trait of the current trait, and so we wouldn't take this path and we would do the other behavior, and this winds up getting rejected. We can look at visit const now. This is somewhat structurally similar, but slightly different because our internal representations of types and consts are not the most unified thing in the world, but we're working on it. Going through this and preparing this talk, I encountered many places where I thought it would be lovely to spend 3 months cleaning up the compiler because it would make the talk flow a lot nicer, but I did not have that kind of time. So we have the feature gate. If features.mingeneric_constags is enabled, that's not super important. The main thing mingeneric_constags does is it lets you use associated constants in the type system, which is good stuff and highly desirable. And that kind of makes sense in this context. We want to special case associated types. We want to specialize associated constants too. So feature gate kind of makes sense. If you weren't already aware of this feature, then reading the compiler code would give you some idea of what it's all about. Then we have this extra junk. I don't know what my next slide is. That's what my next slide is. So in the previous example, we wanted to check for associated types. Here we want to check for associated constants, and for jank reasons, we're doing it differently, which we should fix, but I did not have the time to do so. So starting off, we have this UV, short for unevaluated. and we have this def, short for definition, which is kind of jargon. Generally, it corresponds to some identifier for an item, but not quite, but mostly that's a good enough intuition. So in this context, the item we're talking about is we have our usage of an associated constant, which refers to the associated constant in the trait super below. We then want to look at the parent item of the associated const, which in this case is the trait super. And then we want to make sure that the parent item is actually a trait. And if so, that means we have a constant, and its parent item is a trait. It's probably an associated constant. Cool. And we can do another example where it's not an associated constant. So in this case, we have a path to just some normal const item inside of a module. We look at its parent, and it's a module, and then a module is not a trait, so this does not actually, we do not take this code path. Oh, my slides are in the wrong order, that's cool. What is going on right now? Do I have like 5 duplicate slides? Okay, cool. The rest of the code we were looking at, after we go into this code path, is pretty structurally similar to the associated type stuff. We have the same is super trait of current trait thing going on. We get the trait ref slightly differently for weird jank reasons that we should fix, but I did not have time to do so. And this is the line that crashes, getting the trait ref. Cool. What was I trying to do with this example? Oh, yes. So in this example, we have a case where we're using an associated constant, but it's not in a super trait. And this is an example that we want to reject, because we're using self, but it's not in a super trait. We can go through this example again. The item we're referring to is in the trait super. Its parent is trait super, so we take the code path. The trait ref in this context is the self as super. And then when we check if it's a super trait of the current trait, it's not, because foo has no super trait. I should have picked a different trait name. Cool. So we can go back to our original crashing example. In this case, there are no associated constants. There's not really any constants anywhere. This is kind of confusing. The first thing to notice is that we have a default to a const block, and that's implicitly put onto the trait foo. So if we go through and step through the code again, the definition that we're talking about is going to be the const block. The parent item of the const block is the trait foo, and trait foo is a trait, so I guess this is an associated constant. And I have no idea what the trait ref for that const block is supposed to be, because it's not an associated constant, and so everything just completely explodes. So this is our full code that we've been looking at that has the source of our bug in. We first start, check if it's an associated constant. If it's an associated constant, then we want to figure out what the trait is and what the self type is. And then we want to check if it's a super trait of the current trait. That's the general logic that we're working with here. And the thing that's kind of going wrong is we're not actually properly checking if it's an associated constant or not. It's some random other thing. So we need to figure out how is it that we can actually check if it's an associated constant. And we already have an existing check for, is this a trait? So maybe we can just do something similar to that for checking if it's an associated constant. If you were actually doing this yourself, you'd open up the Rust docs and you'd look at this def kind type to figure out what kind of things we have, and then scroll through it. Doing that in a slide seemed kind of annoying, so I didn't. But to kind of spoil things, there is an associated constant def kind that we can just use. So we have the previous code on top, and then we have our line we've added, where we're kind of copying the structure of the check that a trait is a trait. So even if you don't really have a good understanding of like what def kind is, what a def ID is, all of that kind of stuff, from the surrounding context, you can kind of puzzle together like what the right magic incantation is to do the check we want. We get the kind, we check it's an associated constant. And so now we can go back through the example. We have the unevaluated const block. We check what kind it is. In this case, it's a const block. And that is not an associated constant, and so we don't take this path at all. We've done it. We've fixed a bug in the Rust compiler. If you are actually going to properly contribute to the compiler, it might be useful to make a PR with this change and not just keep it on your hard drive and never do anything with it again. But for us, I'm not going to go through the process of that in this. So that's kind of roughly what fixing a small-ish bug in the compiler looks like. Things can vary a lot. There are sometimes very difficult issues. There are sometimes things that are much easier than even this. Things vary widely. The compiler is also quite big, and there can be unclear interactions between different stuff. So it can be very difficult to tell how difficult an issue is on first glance, even for people who've been doing this for a long time. So highly recommend, if you're going to contribute to the compiler, you should reach out to people and be talking and getting involved in not just the technical process, but the surrounding community of compiler developers and language designers and whatnot. The other thing is that because the compiler is so big, it does introduce difficulties that aren't present in smaller software projects. If you're doing a small project by yourself, you can kind of fit the whole thing in your head. Fitting the entire compiler in your head is not really possible. There's just way too much stuff. There's also just tons of stuff that needs doing. There is effectively never a shortage of work that needs to be done. So if you're ever wondering, like, well, what is it that I can do? It might be hard to find something yourself, but talking to people, people can find you stuff to do. People can find you stuff that's like an appropriate level of difficulty. People can walk you through things. There's lots of resources and stuff. Talk over.
Testing. So we still have a good 10 minutes left in this slot, and I think this is actually the kind of talk that is very appropriate for people asking questions, especially those of you that have been interested in getting involved with the Rust compiler. So we have Boxy trapped here for just a few more minutes. Who would like to ask a question?
Hi, thank you for the talk. Do you think fixing a crash is a good first contribution to the compiler?
I think so. It gets you to do a lot of really important things. I think one of the main things you wind up doing when you work on the compiler is you just spend all your time debugging it, because it's doing weird stuff, especially because it's so big that there are just unclear interactions. So yeah, I think, and it also takes you to random places in the compiler. It's hard to just start and open some random file and like find something to do. And also, if you're trying to work on some feature, that also requires having a sort of general understanding of how different parts of the compiler might fit together, which you don't necessarily have when you've not done anything on the Rust compiler before. But fixing a crash in the compiler gives you a very clear backtrace. Go look at this part of the compiler, and then it can be very self-contained. If it winds up not being super self-contained, that's where having people you can talk to comes in, because they can guide you towards bigger, more involved changes. But yeah, I think crashes are a very good place to start.
All right. Who else we got here? I see one hand here, another there. Sorry, I lost track. Okay, green shirt.
What's the best way for people to get onboarded for compiler dev? Like, is it easy to just, go clone a Git repository and cargo build, and then you're building the compiler from scratch?
You do Git clone it. That's a good first step. Sometimes it takes a while because it's big, which brings us back to compiler is big. We don't use cargo directly. We have a wrapper script which invokes cargo, but all of the commands wind up being the same. So instead of cargo build, it's x build, and instead of cargo check, it's x check. Instead of cargo test, it's x test, which can be a little bit confusing at first, but it's everybody who currently works on the compiler, of which there are a great deal of people, have all had to go and learn that, and will be able, and they use it like every day, so they'll also be able to talk you through it. So it's a little bit scary, but it's fine. You'll pick it up pretty quickly.
Very good. All right, who's next? Let's see, I see one hand over there and another hand over there. Okay, let's start here in the middle. I'll come to the other side. Can you pass that down, please?
Hey, congratulations on joining the compiler team as the team lead.
Thanks.
I wanted to ask about how do you do debugging? Like, do you use the debug macro, or do you use a debugger, or how?
Yeah, that's a good question. I almost included that in this talk, and then I wound up not doing so because I didn't. So we use tracing in the compiler. So we wind up using the debug macro and then also the instrument macro a lot, which actually I've never used tracing by itself. I don't know how much of this is Rust compiler specific. There's a macro which you can put on functions, which does like cool span stuff in the logs. And then you've got the debug macro, which debugs stuff. We use an environment variable, rustc_log, and then you can put a path to a specific module on the compiler, and then it gives you all of the debug statements from tracing, and then you can dump it into a file and look through it. When you're newer to working on the compiler, it can be hard to tell which modules you actually care about seeing the debug logs, and so it's, in my experience, quite common that, and I did this too, you just sort of look at everything, and then you have like a 10 gigabyte log file, and that's way too big, and there's way too much stuff to look at. So again, like if you're going to work on the compiler, you should reach out to people and get involved in the surrounding community, because people can kind of point you to the right modules and help you with the debugging process. I think there's also some kind of tool for doing debugging better, but I don't. Yeah, cold hair person in the front row can tell you about that afterwards. You can like collapse stuff. I don't know. It's cool. I don't wind up looking at debug logs much these days, so I've not used it. But cool. Yeah.
Okay, so you said that fixing a crash is a good way to start, but is there like tons of crashes issues that I can start?
There will be a lot of crashes issues. It will be hard to figure out the right ones. I think like the biggest blanket advice, which I think I've said in response to every single question, is like if anything is like unclear and you don't want to just like pick some random issue, you should go on the Rustlang Zuluf and say hi, and people will be able to find stuff. Because it's, I forget how many issues we have on the Rustlang repo. It's definitely more than 10,000, and less than 10,000 of them are ICEs, but there are definitely thousands of them. So yeah, people should go on Zuluf, and there's plenty of work to do. Oh, and people should feel free to reach out to me specifically, or come find me at some point at the conference. You'll be able to find me because of my stupid hat. Thanks, Ollie. Yeah. That's great. I have so much stuff to put people to work on. It's a real problem.
So thank you for the talk. I'm curious about, so you just described the process of finding the bug in the code and deep diving into the code until you reach the crash point and what you should fix. Can you quickly talk about kind of like a similar reasoning about how you learn about the prerequisite knowledge required for this? So like you explained all these concepts that are present in the compiler, how do you learn about them?
So we have a whole bunch of documentation in like an MD book that explains lots of random bits of information about how the compiler works, called the Rust Dev Guide. It's not the most finished thing in the world, but we're working on that too. And when people come and try and get involved in the compiler and then they run into things which aren't explained in there, that's really useful, because then I know what we need to go and put in it that we don't currently. There's also lots of doc comments on stuff inside of the compiler, which kind of hard to show in a talk, but some of the stuff like what a def kind is like, there'll be doc comments on there that explain the general concept. I didn't check this. I assume there's comments on there. If there's, Ollie's nodding at me, Jana's, okay. There are doc comments on def kind, and And there generally is doc comments. In the cases where there aren't, there might be stuff in the dev guide. If neither of those are true, you can ask on the Zulip, someone will explain, and then you can potentially even be the person who goes and adds that documentation to the compiler, to the dev guide, and then future people won't run into that problem. It is kind of like bashing your head against a wall repeatedly, because there are just like a lot of concepts, and some of them are like not fully explained. But it's mostly just like there's a lot of concepts more so than each individual concept being extremely difficult. There are extremely difficult concepts, like not to lie about what the experience is like. But a lot of the concepts are somewhat you just kind of have to read a comment and then maybe it makes sense, or get someone to explain it to you for 5 minutes and then it makes sense, and then you just kind of know it and it's not a problem anymore.
Thank you.
All right. Anyone else? We still have a few minutes, so don't worry about your question running out of time.
Oh, yeah.
Aha.
Hello. I don't think I have as much of a question, but I just wanted to say for those people who would be interested in this. So I did a workshop yesterday, or I gave a workshop about how diagnostics work, but also a bunch of the people there actually yesterday for the first time contributed something to the Rust compiler after a day of some training, I guess. But what I mean to say with that is that diagnostics are a really good place to start usually, because they only involve a very small subset of concepts that, I don't know, if you try a few of them, like improve a diagnostic here or there, you can actually get a reasonable overview of like what the compiler looks like, and maybe then you can do some of the, well, these type system things which are more involved, though as you could see, it's just normal code. But I don't know, it's a good place to start if you are interested. That was not a question, I know.
Do you have a reply?
No.
Very good. Let's see. I see one hand over here.
Just a quick fun question. Waffle in its talk just previously told us that if we know a Rusty developer to hug them, they are not okay. Opinions?
Wait, can you repeat that?
Waffle said, and I quote, "If you know a Rusty developer, hug them. They are not okay."
Oh, yeah, that's burnout in open source is quite common, and Rust is an open source project, so you could put two together, I guess.
Let's see. I have one more question. I think we have time for one more.
Also, actually, not a question. I was about to raise my hand earlier to say roughly the same thing that Jana already did about contributing to diagnostics. Because that's also what I did first, but the word diagnostics means like the things that produces warnings and stuff. And it's also nice to get into that because you are like less scared of breaking things very badly, because warnings usually don't affect what the code does in the end when you run it.
Yeah, that's true. Yes. That should have been my response, not no. I have nothing. My head is empty.
All right, and that is time. Everybody, let's give Boxy another hand for the time they've taken. And we will have our next talk in about 10 minutes.
Welcome back. For the next talk, we have Bastian, who is a software engineer on Google's memory safety team, if you didn't know that that existed, a member of the Rust-Lang project exploit mitigations team, and a regular contributor to the Rust project.
Thank you very much. All right. So first of all, thank you very much for the opportunity to speak here. I would like to talk about the topic of how we replace common C and C++ libraries with Rust at scale. And this is mostly about the work that we are doing in Google's internal code base, but also touches a little bit on the strategy for Chromium or Android. Yes. So let's start with a quick introduction. My name is Bastian Kesting. I'm a software engineer in the memory safety team, and I have been working at Google for 4 years. Before that, I was studying at Hochschule Munich, and I'm a member of the Rust Expert Mitigations Project Group. Yeah, so let's start with the problem, memory safety and big C and C++ code bases. Generally, we can see that over 70% of severe vulnerabilities in C and C++ code bases stem from memory safety issues. And this is also not only true for only Google code bases, but true across the industry and also, for example, for the Linux kernel. And now with AI getting better at exploiting these vulnerabilities, the situation is becoming a little bit more frightening. At the same time, Google maintains hundreds of millions of lines of C and C++ code, and they often perform pretty fundamental parts, for example, parsing and decoding of images, media formats, and so on and so forth. And as such, they also often process untrusted input. And also Google, of course, like the rest of the industry, also relies on third-party libraries to perform these tasks. Yeah. So a rewrite everything in Rust approach is often unthinkable if we were to think about, for example, the aspect ratio.
Yeah. I am an expert, I assure you. What's the button? I don't use Firefox.
Top center.
Oh, there we are. You know, this is improvement.
Thank you very much. Yes, so a rewrite in Rust approach is often unthinkable. If we were to think, for example, about the Google Photos backend, it would be impossible to rewrite that in Rust. It would be like a very long project, and you have to start somewhere. So the solution that the team that I'm working on is operating under now is to replace unsafe third-party libraries with Rust alternatives. So of course, not every C and C++ third-party library is automatically unsafe, but there are a few tricky ones. And this is basically building on the argument that one of Rust's biggest strengths is the absolutely amazing ecosystem with maintainers who really care about what they build, who don't veer away from re-implementing common like media formats or fundamental libraries in Rust. And they often do that with a better performance. So we have a unique situation of being able to replace some unsafe library with something that is not only faster, but also safer. So it becomes a little bit of a no-brainer. Yes, and also since these third-party libraries are often the parts of the code that perform risky operations, this is actually reducing the risk where necessary. So let's roll out these safer alternatives wherever we can. First of all, I want to speak a little bit about the different flavors of safer alternatives that we have. As a prefix, most of the calling code that we have in Google is C++, which already uses some features, some modern C++ features like AppSite span and bounce checks, so a hardened standard library. So we already do what we can from the C++ side to move towards memory safety. Yeah, this is just to keep in mind for the next few slides. So the first flavor of drop-in compatible, the first flavor of a safer alternative is a drop-in compatible safer alternative, where the Rust library exposes the same API as the C library, so it just exposes the same symbols. And this allows us for easily switching out the the C dependency for the Rust dependency. Yeah, the benefit is that it's easy to adopt, and the only downside is that we don't really get rid of the unsafety related to the C APIs. So often C APIs induce tricky situations, for example, around handling lifetimes, destruction orders, and we don't fully get rid of them with this approach, and our Rust needs unsafe to interact with C. Yeah. The other safer alternative flavor that we have is to wrap a Rust API in C++. So the way that we do this is that we import a Rust library and we give it a C++ API. How exactly we do this, I will explain in a moment. But this means we have a wrapper that is close to the Rust library and to the Rust API. It's relatively easy to create these wrappers. They are not that much code, you will see. And the only downside is that when we want to roll this out through the code base, we now have to go to the callers and we have to rewrite them. So if they use libpng before, we would have to rewrite them to our safer alternative that provides the same functionality as libpng. So yeah, how do we wrap these Rust APIs? The tool that we use here is Crubit, which is developed by a partner team in Google, and it provides a way to bridge C++ and Rust. The way it works is that it's generating FFI bindings. So for the direction of C++ calling Rust, it will generate a C++ header that allows us to call into Rust. For the other direction, it would generate Rust functions that allow us to call into C++. And the interesting thing about Crubit is that it allows us to also bridge functions and constructs that don't necessarily follow the extrinsic calling conventions. So Crubit is able to understand like a subset of Rust and yeah, make it available to C++. So this means we can use Crubit to put a fairly nice C++ API in place that allows us to call the underlying Rust. Yeah, and also values from either language can be moved across stack and heap memory in Crubit on either side of the FFI boundary. So how do we get the second flavor that we mentioned, the drop-in compatible replacements? And this is mostly through the absolutely amazing Trifecta Tech Foundation, who among other things are working on zlibRS, libc-std.rs, bzip2rs, which are all projects that we are rolling out. The benefit here is that the rollout is much faster, as I mentioned before, because we just need to update the build dependency and basically link in the Rust version. Yeah, and also another thing that we're exploring is that AI can potentially help us to create these drop-in replacements much faster, or makes it much cheaper. So the research space of C2 Rust translation is quite active, and yeah, we're also interested in that to translate code from C to Rust. Yes, one thing I wanted to talk about is that there was always this very scary thing, this very scary question when rolling out such changes is what if Rust returns different bytes, or what if the Rust library behaves different than the C version, and someone depends on this. So this is something that we thought about, for example, when rolling out the zlibRS project, which returns different bytes than the zlib version that we were using before. And it's quite scary if you think about it, because you might have some logic that depends on this. But in practice, after having rolled out like a lot of these safer alternatives across various domains like compression, image decoding, but also parsing of JSON and so on, we found that we mostly didn't find any issues with this. And this was mostly due to the fact that the people who depend, or the consumers who depend on numeric stability or on exact behavior, they have been often bitten before by library upgrades already, because libpng, for example, also doesn't guarantee you numeric stability over different versions. So when a new version was pulled in, they were often already bitten, and they were aware that they depend on exactly this behavior. Yeah. And also, engineering culture is really a door opener here. There's one rule internally at Google that I wanted to share that was really helpful for us here, and it's called the Beyoncé rule. And it goes, if you liked it, then you should have put a test on it. Yes, so the idea here is that if someone depends on a certain behavior of a third-party library, they should add a test for it. And this is also like helpful for library upgrades. It's helpful for when we roll out. And the way that we perform these rollouts is that we migrate as a single consumer, and then we run all the tests that touch this target. So we basically run the transitive closure of tests on this target, and we go through the failures and analyze whether they are relevant or not, or whether they depend on numeric stability or not. Then if they don't depend on the numeric stability, we are able to, in the same commit, switch out the version and update the test dependencies. We send that to the code owners, and they can give us a feedback whether that looks legit or not, and then we have it rolled out. So yeah. So what did we actually roll out? This is an excerpt of what we did, but we started with sorted JSON and replaced JSON parsing. We rolled out Symphonia, an audio decoding library that we use for MP3, FLAC, and Ogg-Vorbis. Image PNG, which is also used by Chromium now. So the PNGs in Chrome browser are now rendered with image PNG. We rolled out a few compression libraries like zlibrs, bzip2rs, Rust broadly, ziprs, XML parsing we also did. And ZoonJPEG for JPEG decoding, and there's a replacement for libjpeg turbo. Yes. And another thing that I wanted to talk about is that we see that this is a shared problem, and we would like to enable people to follow what we did and also try to bring Rust into their C code bases. And we are open sourcing these wrappers that we have. They are in a GitHub repository under Google/safe bindings. They will be extended further. Currently, it's not all of the ones that we have available, but we will make them available step by step, and we will also build them in the open. And currently, they work with Cargo and CMake. This also features an open source buildable version of Crewbit, which works with CMake and Cargo. Yeah, and I would be really interested to chat with anyone who's interested in this on what would be requirements for you to adopt this. What kind of build system support would be interesting? Yeah, I'm open to chatting. So thank you very much. And as I mentioned, please reach out if you're interested in adopting these safe alternatives, and also check out Trifecta Tech Foundation. They do cool stuff. Thank you.
Cool. I think we have a little bit of time for questions. Hard to see with that light.
Thank you. I want to ask, in Chromium, there's this famous rule of two. If you have Rust library and you put the wrapper around it, the C++ wrapper, is it considered that it breaks the rule or not? Or how do you balance this similarly with unsafe code too in Rust library?
Yes, so in Chromium, basically something that has a C++ wrapper is considered compliant. You don't need a separate process to parse, for example, JSON if you use such a wrapper. So we consider it safe, this thing. It's kind of as safe as it gets because we somehow need to call it, and we somehow need to hand off at some point. Yeah.
Thanks. Do you use differential fuzzing to compare the two implementations, or is that too noisy because you already have tests for things that are important and you don't want to be bug for bug compatible?
Yes, that's a good question. So for some things we know they are different. So for example, for zlibrs we already knew it was different. So differential fuzzing was not very helpful. Also for XML it was a little bit tricky because what libxml accepts and what quickxml accepts is a little bit different. So there we didn't really use it, but for things where we really want to have equivalence, for example, for Z-standard compression, we want really the same results for every input and everything else is a bug. There we are using differential fuzzing.
So first of all, thank you for the talk. My question would be, did you run in any special linker problems that you could share?
Linker problems? I don't really think so, but also this is nicely abstracted away from us because we have a toolchain team that we can talk to. But we didn't run into something specific. If you have something concrete, we can chat about it. If you have an idea of what could go wrong.
Sure. So there's one thing that we stumbled over is when you are integrating Rust libraries as static libraries and use the standard library, then standard library symbols can have problems with each other. And the solution that we found was to create an umbrella Rust crate that sort of creates one static library that would be then link. But I was wondering whether there are other solutions to that issue.
Interesting. So yeah, this I cannot really answer to this because we didn't really have that issue. But Taylor has an idea. Yeah. Do we have a microphone?
My question is along the same lines, and actually part was exactly what he said. The other part is what are you using to do the compilation? Are you calling to cargo, or is it GN handling it internally by calling RASI?
It's different per project. So Chromium is built with GN, and internally in Google we're using Blaze, which is like the Google internal version of Bazel. Yeah, the Google build system.
If you want details about our linker setup, you can chat with me afterwards.
Yes, Taylor is a good person to talk to about the linker setup.
Thanks for the talk. You said that you can also call into Rust code which is not extern C declared. And in my understanding, the calling convention of default Rust is not like standardized. And I wonder like if there's any problems with that, or how do you solve it?
Taylor is the right person to talk to, but
all right.
Yes.
I'll leave my ears on, so you can come find me afterwards.
Hi, so thanks for the talk. I wanted to ask, since you're using quite a bunch of like open source Rust libraries, is Google already kind of like sponsoring some of the maintenance of those companies, or has it considered like financially donating to some like open collective or thanks to dev or something like that?
Yes, so Google is funding Trifecta Tech Foundation, for example. And also other open source projects, and it's something that we also look at because we're consuming a bunch of awesome stuff from open source, so we should give back. Yes.
Okay, thanks.
Cool. Thank you, everybody.
That's a wrap.
It's an hour and 15 minutes, if you didn't hear me, until 2 or 1400. There's also a Women in Rust meetup in the Rays area by Spaze. Everyone that is interested is welcome, so go attend that, and we'll see you in a bit.
Oh no. Doors are closing in. Oh. All right. Welcome, everybody. I think the last time I was up here, I said, how was lunch? And everybody was like, when I understand now because it was way too early. Sorry about that. So how was lunch really? Yeah! Oh, glad to hear it. I myself stuffed myself silly, and I'm very happy to sit down and watch somebody making some great content again. So wanted to just throw a couple of shout-outs. Again, I guess I'm the shout-out guy. We have a few gold sponsors I want to mention today. JetBrains, which we've already had some folks from JetBrains up here. So thank you very much, JetBrains. Hey, there you go. Zed Industries is also on the list of people that we'd like to mention. Thank you very much, Zed, for the sponsorship. And also, a big thank you to Google for being a gold sponsor here. We also had some great talks from Googlers here.
All right, welcome back, everybody. Next up, we have Jin, who is the compiler team lead at Ferris Systems and enjoys doing evil and deranged things to computers.
Thank you. So this talk is called Precise, Consistent, Reliable Code Coverage. I wrote it for this event, but hopefully we'll give it again in the future. So when you see that, you might ask, what is code coverage? Why are we having a whole talk about this? Don't we know this already? And if you use code coverage, you're probably used to seeing something like this. So this is a CodeCov bot that has posted on a GitHub PR. It says, in this PR, we have had some amount more lines that are tested, some amount more lines that are not tested. And generally, people who set this up don't actually care about the number. They just care if it goes up or down. Right? It's giving them an indication of whether they have more or less tests after this change. I want to talk, in this talk, about deterministically flaky coverage. What does that mean? Well, I work for Ferris Systems, and specifically I work on Ferosine. Ferosine is a Rust compiler. It is upstream Rust with just a few more tests added so that we can run it in safety-critical systems, cars and industrial equipment and metal equipment and things like that. And in this compiler, part of the language that is intimately tied to the compiler is core, the core library. And as of November last year, we started shipping a certified core, which means that you can use those functions in your embedded or safety-critical app. And one of the requirements for shipping a certified core is that we need to have a bunch of tests for it. And in particular, the standard that we're using is IEC SIL2, which means that we need to have line coverage for every function we certify. So if we have 100% line coverage for every function, that means that we can ship our release. And if we have anything less than that, then we can't ship a release until we have full coverage. So here's an example of what that looks like. This is a report that shows that we have 99.5% coverage. This is pretty good shape. This needs like maybe a week of work, but in general, like we could release with this. There are several things that are weird in this report, and I'll come back to them. But first, let me tell you how I ended up looking at coverage at all. Here is another coverage report. So this only shows 83% coverage, which is way lower, and that means that we must be running fewer tests for the same code, right? No, these are the same code, same tests, same person, same laptop, same checkout of the compiler. The only thing that has changed is this bootstrap.toml thing. So Bootstrap.toml is a configuration file. You can think of it as similar to cargo config.toml. It has a few user-specific settings, and it's used by the Rust compiler's build system. And so what is the difference between these two files that causes such a drop in coverage? This is it. This is the whole thing. So channel is what you see in the output of rustc-version. So the one you're used to seeing is stable, or maybe nightly. You'll see like 1.91.0-nightly. And I hope that it's clear by now that something is very wrong here. At this point, we spent about a week tracking down every possible thing that could be affected by the channel. We looked at config release. We looked at Bootstrap's Rust C shim, don't ask. We looked at Cargo's parsing of Rust C version. None of those looked relevant. And also, only half of the people in the company could even reproduce this change, this drop in coverage. So we started looking at more things. We looked at remap debug info to see if that could make a difference. We looked at frame pointers. We looked at the Bootstrap test stage that was used. Also, don't ask. We looked at the debug info level that the standard library was compiled with. And none of this made a difference. So this is where I come in. Jorge posted his message in August 2025, and I joined the company in September. This was my second week on the job. I had been there for 7 days. So in a second, I'll show you what I tried to figure this out. But first, I want to go back to that no good report. So this shows 99.5%, but there are some weird things in here. For example, that function percentage does not match the line coverage. A little bit different would be fine, but this is a lot different. The core percent doesn't match the overall percent. This is supposed to be showing coverage for core, so we would expect these two to line up. They don't. We have a lot more functions than we have lines. Generally, functions are made out of lines, so that's a little bit concerning. You can't tell this from the report, but core future is actually not certified. You're not allowed to use it in a car because we haven't tested it. So the fact it's appearing in this report is pretty weird. And then finally, we have no numerator or denominator for that 99.5%. We don't know what it's out of. I didn't spot any of this. The only thing that I noticed was that our 99.5% didn't match our 80%. And I was told this is because of monomorphization, because you will have the same source line that gets substituted with different generic parameters. And so you will have multiple functions in the binary for every source line. I was like, OK, sure, makes sense. So I went in a different direction. I looked at how we generate our coverage report. This here is a little diagram of our pipeline. We start by compiling core tests with C instrument coverage, which is built into the compiler. Then we run cargo test. LLVM has instrumentation that will detect which functions are called during cargo test. It will write to these profile files. After the test, we will collect and merge these profile files into a single prof data that's optimized for reading instead of for writing. And then we will take that prof data, we will export it to an info file for reasons. And then we convert that info file to an HTML report that you've already seen that's easy to read. And we have already seen that the HTML is wrong. And from looking at it, we knew that the info file was wrong also. We knew that there were functions in the info file that should not have been there, which gives us this diagram. So by the time we get there, something has gone wrong. And because we're running with the same source files, we know that that part of it is right. So something in the middle is going wrong here. OK, let's come back to that. Let's take a closer look at the report itself. This here is a covered function in alloc. It's called from size align. You can see here that there are various lines in the function. Most of them are marked green, which means there's executable code that is tested. And a few of them are marked white, which means that they are comment-only code, and we don't need to test them because there's nothing there to run. And on line 78, it calls this function is size align valid. And because we know that call is executed, it's green, that means that is size align valid is also green, as you can see here. Oh dear. So the fact that this is white instead of green means that LLVM thinks there is no executable code here. It thinks this entire function is a comment. And because it thinks the entire function is a comment, that actually means we cannot trust any part of our pipeline. Not only is that 99% wrong, but it has no relation to reality. There is no correspondence between that 99% and the thing that we actually care about, which is test coverage. So that's not great. And the reason I mentioned numerator and denominator earlier is because if we had that on the report, we would have spotted this right away. We would have known that the 99.5%, which looks good, is actually the one that's wrong, because it's the one that's missing things in the denominator. We would have seen more things in the denominator in the other report, and that would have told us something's weird here. So why does this happen? Let's go back to our diagram. Something here is wrong, and debugging Rust-C or Cargo or, God, LLVM sounds hard and complicated, and I don't really want to do it. But what sounds less complicated is looking at what's actually in these files. So let's take a look at what's inside this prof data file. This here is LLVM prof data. When we're saying show me the contents of the file, show me all the functions in it, and look for this specific function called isSizeAlignValid. This is the one that was marked white when it shouldn't have been, and then demangle the symbol. And it shows that it's there. It shows that it has 3 executable lines, and that's instantiated 1,500 times. That's a little concerning, but sure. So it's there. It's in the prof data. Is it in the info file? No, it's not. If we look for that function name in that info file, we get 0 hits. So at this point, our diagram looks like this. We know that the prof data is good. We know that the info file is bad. So whatever goes wrong has to happen between those two. And the only thing that we do between those two is to run lcov export. So how do we run lcov export? This here is an invocation of Bootstrap, the build system for the compiler. It says test the core library, collect coverage for it. Don't run the doc tests, because those don't work right now. Show the commands you're running. Build the profiling instrumentation from source, and generate a HTML report after you've done all that. That will print a bunch of spam. And then after it's printed a bunch of spam, it will show us the exact command it runs. And the command it runs is llvmcov export with the prof data file into the lcov format. But there's this other thing here, which is the core benches and the core tests. Why are those passed as an argument to llvmcov? Well, if we look at the help file for llvmcov, it says those are covered executable or object files. And I'm getting a sinking feeling at this point. And the reason I'm getting a sinking feeling is because it means that what I thought was going on, which is this diagram here, actually it looks more like this. The binary that we've compiled is an input between the prof data and the .info. The prof data is not the only thing that we're reading between those two. Well, that's another place for things to go wrong. So let's go look at that place. Let's go look at how Bootstrap generates the arguments to lcov. This here is slightly simplified, but mostly original code from Bootstrap. It says, look in the cargo target directory for every file in there, if it's executable, and it is a file and not a directory, then add it to our arguments. But it also says another thing. It says filter .so files. What is a .so file? So SO stands for shared object. They're shared because they're reused between many different processes. So here I've shown the startup logic for the core tests binary when it's executed at runtime. We have the dynamic loader, which will load in the core tests executable in your target directory. But we'll load other things too. It will load the libc runtime, and it will load the Rust standard library at runtime. And then it will put all 3 of those into the same address space so that you can call into functions as if they were compiled together. And the reason that we do things in a separate shared object file is because Bootstrap likes to use prefer dynamic, so it's not relinking the same file over and over. Linking takes time, it takes CPU time and things like that. And so because Bootstrap is linking so many different executables, it wants to avoid doing that each time, so it puts the standard library in a separate file. So that's good for disk space. It's good for CPU time. Unfortunately, it also means that we have just told LLVM-cov that we don't care about coverage for anything in the standard library. This is a problem, because the original thing we wanted to do was to get coverage for the standard library. So we have one last piece of the puzzle here. We had a 99% report that was good, quote unquote, and then we had an 83% report, which showed a lower percent. Why were we getting two different reports? And now I have to talk about inlining. So inlining is a process where the compiler will take the function that you're calling, and it will move parts of it to the caller function. So here I have an example of this struct point, and we're going over a grid. For every xy coordinate in the grid, we create a new point and do something with it. And on the left here, we have this new point function, which in a real code base would do more than just create a struct. But the calling that new point function actually has some overhead at runtime, and it has an optimization barrier. It makes it harder for the compiler to do its job. So the compiler tries to get rid of that barrier. It tries to move it inline to the middle of your hot loop so that the loop runs faster. And so what that means is that sometimes the function will get inlined into core tests, and it will get instrumented. And sometimes the function will not get inlined, and it will not get instrumented. And whether that happens is up to the compiler. Inlining is not stable. It is somewhat deterministic, but only in the sense that, like, if you run things in the same order on the same thread, it's deterministic. In practice, this is basically up to luck. So that's not great. So we actually have multiple bugs here. Our first bug is that we're not instrumenting libstandard.so. This is the thing that we wanted to collect coverage for, and we're not collecting coverage for it. But the second, and yes, it is true that if we have, the core tests binary and we instrument everything in the core tests binary, everything there will be covered because we're running it. It's a test runner. Everything in the test runner is indeed tested. That's how test runners work. But we have a second problem here. The second problem is we didn't notice that we had a bug. We thought that we had 99.5% coverage. We thought that we were good to release, and we weren't. And the reason that happened is because we trusted LLVM. We trusted it to tell us which functions we care about. And this one is harder to fix because it's not as simple as just saying instrument this additional binary, because maybe there's other binaries that we're missing. Maybe our build is weird in a way that we don't know about yet. How can we know? And we actually do have a way, in the case of Ferosine, to know. We know exactly which functions are allowed to be used inside of a car or a safety certified system. So this here is a report of everything in the core library subset. And this would span in the real report, several thousand functions. And we hand this to our safety assessor, and we say that our certification is valid for these functions. And we've been doing this for several months now. So we can take this, we can use this to double check our work, right? We already know which functions we care about. We can compare that to what LLVM thinks we care about and play spot the difference. So we did that. Here is a tool that I wrote that will show a report of everything in the binary. And notice here, not only are we showing things that are tested and partially tested and untested, but we're also showing things that are ignored. And that fourth category is the new thing we're getting that wasn't there before. This says that LLVM thinks that this should not have coverage, but we, from the people at Ferosine, think that it should have coverage. There's a mismatch here. And this allows us to look at the mismatch and make a judgment as to why it's there. So in this example, I've shown an implementation of clone for the infallible struct. Infallible is an enum with no variance. That means that you cannot construct it. If you ever end up with this value, it's undefined behavior. It's kind of like the never type. And we can look at this, and if you construct an instance of infallible, something has already gone wrong. You already have undefined behavior. And so the compiler knows that it actually doesn't need to generate this function. It knows that this is just always dead code. And now that we have this report, we can look at that and say, okay, that makes sense. We couldn't do that before because we didn't know that it was being emitted. Now we do. Right. So what does our pipeline look like now? It looks like this. It's mostly the same. We still have our core tests. We still have our profra that we're combining into a prof data. The thing that's new is the symbol report.json. So this is going through all the functions in core, and it's generating a list of them that we can compare to. How do we know what's validated? Well, we have this attribute that we added. This is called a tool attribute. And this tells the compiler, hey, we have this bit of code with a little bit of metadata. Attach that in your internal data structures to this function. But something has to read those internal data structures. So what did we do? Well, we wrote a Rust driver. This hooks into the compiler itself. It says run macro expansion. After you have run macro expansion and you know everything in the crate, collect a list of those things, write them to a JSON file so we can analyze them further, and then just stop compilation. We don't need to do anything further. What do we do with that data once we have it? There's a handy-dandy library called LLVM Prof Parser. It's written by Daniel McKenna. You may better know him as the Tarparlin author, or XD09642. What you may not know is that he's a rice farmer. He grows rice in large flooded fields, and he writes about this in detail on his blog. So if you're interested in that, check it out. Right, so we use that library, LLVM Prof Parser. We will read the prof data file. We will do some analysis of that file. We will load our JSON report of all the functions in core. And then finally, we make a pretty HTML report that you've already seen that shows us which functions are ignored. OK, so this only touches on the complexity. There are a lot more things that I didn't mention, which is why we need the binary paths in the first place. It's because it needs dwarf debug info, which is a whole rabbit hole. We have this core tests are actually linked as a separate crate. So most crates can run tests in just like a tests module and then run cargo tests. That doesn't work for core tests for weird reasons to do with lang items. Don't have time for that. I didn't talk about the many, many caching issues we had with profiler built-ins. It turns out that if you try to instrument core, that ends up instrumenting profiler built-ins. But you can't instrument profiler built-ins because that is the profiler, so that's a problem. And then we have other issues going on here, like when we monomorphize these functions, we will have thousands of them for the same source lines. How do we map them back to the source lines? That's another thing that's complex here. Yeah, so in summary, code coverage is surprisingly complicated. Sometimes you need to understand the details of your system. Sometimes it's not enough to just look at a high level, and you really need to know like what's going on under the hood. And in those situations, it's not enough to guess and check. There's too much code here. I couldn't possibly have read it all in time for this release. Instead, I had to work backwards from the final issue to the things that were causing it. And I had to be systematic, and I had to make sure that I was verifying my assumptions along the way. And if you're interested more about that, I can recommend you my workshop, which happened yesterday, and I'll be posting more about on the Discord. Right, you can find these slides online, and I'll post them in the Rust Week Discord afterwards. Thank you.
Cool. We have a bit of time for questions.
Thank you for the wonderful talk. This was an incredible debugging story, and I'm grateful that we got to experience it with you. But I'm also curious, how would you recommend that we think about building tools such that these kinds of epic debugging stories are not as often necessary?
Yeah, so there's a couple of things. The first one that comes to mind is to have a list of, just to like show more info, right? Like the numerator and denominator thing would already have saved us like several weeks. And that would have been really easy for whoever generated the report to make. The other thing is to prioritize simplicity. So if we go back to the final thing I came up with here. There are a lot of nodes in this diagram. Part of this is because we're under like time pressure and hot deadlines, but part of this is just because the tooling's complicated. Yeah, I don't have all the answers here. I think a lot of it is we need to like rethink how our computing works. But I do think like prioritizing simplicity is something that would help with these things.
Cool. Do we have any other questions? Hands up down here.
Thank you. It's nice to have a closure for the workshop, sort of. You mentioned part of the problem is that you are testing libstd and it's supposed to be excluded. So will there if we abstract that away? I mean, if I have some code that is not libstd, at least, will I need to change something to make sure I don't run into this problem, or at least that much?
Yes, this
And
problem
will it
generalizes.
be-
You might have this problem in your own coverage tooling. Yes.
So, what should we do as the users?
Well, we need
Like-
better tooling. So I've written something like this, and I think something like this could be made general purpose. I work at Ferris Systems. We do work on contracts, so if somebody's interested in that, please reach out to me at a salesperson. So this has turned into a marketing talk now. But yeah, I mean, I think that really is that we need better tooling. We can't just like trust the tooling all the way through.
Okay, well,
yeah.
Thank you.
Hi, so I was wondering if you need coverage for every line of code that is used, how do you deal with things like option T? How do you test arbitrary T?
Yes. So the short answer is that the standard doesn't mention that. So we're like, well, if we cover the line, it's probably fine. The long answer is that eventually we're going to have to do statement and branch and MCDC coverage. And at that point, we will have to start thinking about it. And at that point, writing our own tool will really come in handy, because we can look at every monomorphized function and see was every branch of this monomorphized function covered, not just the aggregation. If we go back to the report I have here, when we parse this prof data file, the prof data actually has every monomorphized function. The aggregation from the monomorphization to the source line happens when we generate the HTML report. So we have the opportunity there to attach more data.
I think we got one over there. Oh, front row too.
It's a lot of stairs.
You said MCDC coverage in the previous answer. What does that mean?
MCDC stands for Modified Condition Decision Coverage. So the three main types of coverage are line coverage, which we've already seen, branch coverage, which is like every if and else, and sometimes if and else can be on the same line, so they're different. And then MCDC is every condition in an if. So if you have if A and B, not only do you have to test the if block and the else block, but you also have to test A being false and B being true, and B being true and A being false.
And follow-up question, would like formal methods and proof solvers be relevant technology to trying to solve like the MCDC coverage?
So there's like an analogy between MCDC and symbolic execution, I think, but I think it's only an analogy. Like they're trying to test the same thing, but I think the tools are different. Now we could do formal verification if we want to, but that's harder because now we have to write a spec, right? We have to write it out in formal detail.
Thank you.
How do you do code coverage on closures that have generics in them?
Closures inherit generics from the parent function, and so they're cogend with their parent.
Right, okay.
think we got one in the middle here. Delay while we run the mic.
Thank you. Yeah, so so I presume you're testing the existing Rust compiler and not your own compiler, is that right?
Our compiler is a small fork of the upstream compiler. So we have a few things that are different, like additional tests and additional lints, but it is almost entirely the same as upstream.
Yeah, so I suppose you're not really interested in testing how the language works, and more so just that the compiler does what you'd expect for the language, is that correct?
Yes, so this is a question we get a lot, which is how do you qualify a compiler if you don't have a specification?
Yeah.
And the answer is we wrote a specification. It's called FLS, Ferosine Language Specification, and we actually donated it to the project. And I think the acronym is just FLS now, and it doesn't stand for anything. But fundamentally, the thing we need is to have documentation and to have tests that our compiler matches the documentation. And if we have those three things, then we don't need the ISO committee to be involved.
And then one last thing, so is that similar to the Rust reference, or is that?
It is similar, but in more detail. So the Rust reference tries to document things that will always be true about the language, even in the far future. And the FLS documents things that are true today, even if they're unstable. Thank you.
Cool. I think we have time for one more if anybody's got one. Otherwise, up here on the...
Yeah, I might be misinterpreting this, but are you basically trying to tell us that for any project with the current tools, we can't really trust code coverage?
That's right.
Okay. That's quite a problem.
Yeah, I think a lot of people don't look at there's too many tools to look at all of them, right? And so you just have to assume that they work, but often that's just not true. Yeah.
So if you're trying to write a more safe compiler, wouldn't you just put it in the mainline compiler?
So a lot of the things we do are under a deadline, right? So upstream really cares about backwards compatibility and not merging anything that they will have to change in the future. And sometimes if we have a customer contract, we just can't wait that long, right? So our goal is always to get things upstream. We want people to have better coverage tools, but we also have a deadline.
Thank you.
Mm-hmm.
Cool, and I think that's it. So thank you very much.
There we go. All right. Hello, everyone. Welcome back. Our next speaker is Xavier Dennis, pronouns he, him. Not unlike me, he's been writing Rust since 2014. Hey. Oh, yeah.
Oh, geez.
Oh, geez. We're old grandpas now. He has a PhD in the verification of Rust programs and has been developing the Crusoe verifier. So let's give it up for Xavier.
Hi, everyone, and thanks for having me here at Rust Week. It's really awesome to see a lot of really cool talks about the compiler and talking with everybody. A little bit about me. So yeah, I've been writing Rust since 2014. I remember back when there was like auto-boxing and things like that in Rust. I dabbled in writing a kernel. Didn't get very far. I think everybody was trying that at the time. Since then, I did a PhD on the formal verification of Rust programs, where I wrote the Crusoe program verifier, and that's been a lot of fun. I've currently moved on, and I'm working at TurboPuffer, where we're building a search database backed by object storage. Additionally, if you want to talk to me about this after the talk, I do a little bit of amateur software archaeology. I've been rebuilding the very first Soviet programming language and its accompanying VM, so that's a fun subject. Today I want to talk to you about a kind of fun little story that happened when I first joined at TurboPuffer. And it's a story about program optimization in Rust and about databases. A big thing about my background is I actually don't have a lot of database experience. I mean, I took like the database class in my university during my bachelor's. That was basically it, right? So there's a lot of database things that I've been learning along the way. However, I do know Rust fairly well, I would say. So there's still some things I could apply and some intuitions I could bring. In any case, we have this little query up here, right? So what we're trying to do is we're trying to search some text. We have some ranking function, in this case BM25, which is like a classic text search algorithm. And we want to apply some filters. And so those filters, we want to restrict ourselves to documents that match some set of conditions, right? Ideally, we want our searches to be fast. If you have a slow search, it's almost useless, right? The problem is, like, over 5 million documents, I don't know, you might want it to be like 50-ish milliseconds. That feels pretty fast, right? This query was taking 220 milliseconds, right? So it's already pretty slow. And we had customers running the same kinds of queries over larger document sets, and it just got slower and slower and slower and slower. So the question is, why is it so slow, right? So I do what I think any good programmer who cares about their performance does and I bust out a profiler. I run some benchmarks, I look at a profiler, I get back something that looks like this. And it's pretty nasty. You get this giant pile of iterators, right? So you're like, okay, well, it's iterator code from the standard library, not really a ton I can see there. But it's kind of frustrating because you just see like a bunch of random stuff. There's nothing very clear there about what
Welcome back. Thank you. Let's say thank you for our sponsors. Espressif is a silver sponsor. Infineon is also a silver sponsor. And also thank you to Oxide Computer Company, another silver sponsor. Next up, we've got Alona, who is a member of the RustDoc team and has been working on RustDoc JSON for the past 3 years. She also helps maintain a 120-year-old car called a Boanerges, which she can correct me on. Also, ask her about it.
Hi, so I'm here to talk about third-party access to compiler state, why you'd want this, how you'd get it, and some challenges you'd face along the way. I'm Alona. I've been working on RustDoc.json for about 3 years now, and this talk comes from a lot of soul searching I've been doing about what is RustDoc.json, why is RustDoc.json, how does it fit into the rest of the ecosystem, what's it good at, what's it bad at, why are people using it and asking for features that don't make sense. So this is the compiler track. Let's start by talking about a compiler. It's Rusty. At a very, very abstract level, Rusty takes your source code as inputs and produces either an executable or diagnostics as its output. But this isn't enough. We want to do more things with our source code. We want to format our source code, and we want to have documentation for our source code, and we want to have diagnostics for our source code for other checks from either linting or dynamic analysis. And the Rust project provides tools for all of these in the form of RustFump, RustDoc, Clippy, and Miri. And these are great tools, and they solve a lot of problems. But even this isn't enough. People have even more things that they want to develop effectively. And there's all these other third-party tools that are not provided by the Rust projects, from linters to check your code is correct in additional contexts, or verifiers to use formal semantics to check that your code behaves exactly as specified, or refactoring tools, or ways to inspect your tools, or custom code gen backend for weird targets like GPUs, or research projects to improve the future direction of the language. All of these are also tools that people also want. And what I want to talk about is how the tools that the Rust project makes works, why third-party tools can't work the same way as the Rust project's ones, and the many approaches that third-party tools can take to try to deal with this. So, going back to Rusty, Rusty doesn't compile your code in a straight shot from source code to executable. It has a number of steps along the way. And these ways of representing your source code that are somewhere in between the source code as an input and an executable as the output. And therefore, they're called intermediate representations. So let's use this function as an example. It just calls foo and bar in a while loop. Now, the first thing the compiler is going to do is pass it into an AST, so it has some idea of the sort of syntactic forms and tree structure that it has. Notice that the comment has gone away. And we have, instead of having to navigate around a string, we now have a tree that is a much more structured representation of fundamentally the same idea. The next thing that happens is it's going to be desugared into an IR called here, where the while loop has been replaced with a loop and a break. So we're getting even more. It's still the same idea. It still has the same behavior, but it's further abstracted away from your source code. Also, at this point, we've resolved the names of functions we're calling. We know that they exist and where they are if they come from use statements. Next, it's turned from still a source-like tree into a graph of various blocks your code can be in and how your code moves between them. This is really essential for borrow checking and reachability analysis and checking that your variables have been initialized before use. So going back to this diagram, we have this compiler. It has all these different ways of thinking about your source code, and these are necessary both to build an executable, but they're also needed for the tools that the Rust project ships. RustFump works by taking this AST and reprinting it in a pretty way. RustDoc works by taking the here and walking over it and emitting it to HTML. Clippy works by walking both over here and mirror and looking for specific patterns to tell you about. And Miri works by taking the mirror and executing it in such a way that will warn you if you do undefined behavior. So how do these tools get access to this intermediate state? And that's really the crux of what I'm talking about. And turns out Rust-C, like any other Rust programmer, is just made of a bunch of crates. And these tools that the Rust project ships can depend on them. They have to use this weird extern crate syntax, which has largely disappeared since the 2018 edition, but is actually still needed to be used here for reasons we'll get to later. But other than that, it's a normal library, and they can create a config that specifies the code that they're compiling, the compiler flags and their dependencies, and then they can run the compiler. And the exact details of once they do with the compiler output aren't really relevant here. The key thing is that all of them need to run bits of the compiler because these tools, they don't want to implement all of this pipeline themselves that they need. There's no reason that Rust should need to implement its own parser. There's no reason that Clippy should need to, that Miri should need to implement its own control flow graph. That would make changing the language and developing these tools much more expensive than they need to be. So can you as a third party do this? And it turns out you can with this one simple feature flag. And if you use feature Rust-C private, your code can link into the exact same crates that are used to implement the compiler, and you can have exactly the same access as the Rust project tools. And problem solved, right? This is great. We can all go home. But turns out it's not that simple. First thing, this is unstable. And this is extremely, extremely unstable. It's like, it has 10 times more breaking changes than like every other Rust feature combined, because any time someone changes the compiler to improve, to add new language features or improve diagnostics or just make the compiler more maintainable, they're probably going to change these APIs. They're designed not to be for building tools. They're designed to ship the compiler first, and if you can use them to write your tools, that's kind of a happy accident. So you need to be on Nightly, and you need to be on a specific version of Nightly because it will change under you. The other problem is we're not getting the compiler from Cargo. When you Cargo build your tool, it's not building the compiler. The compiler has already been compiled when it was before it was distributed to you through RustUp. So instead of statically linking the source code, instead of statically linking the compiler in your tool, that's actually linked dynamically. And this means you have a dependency that at runtime, the Nightly version of the compiler that you built your tool with exists at runtime. So between these, it's looking pretty nasty for third-party tools to use the compiler. We have APIs that break all the time. Here's an example of a pull request to update one of the tools that uses Rust-C private. It's a 2,000-line diff. And this is happening constantly. And projects have died because of this. There was too much maintenance burden
All right, everybody. Our next speaker is Aisata Maiga, pronouns she, her. She has written a thesis about Rust and Spark titled, Does Rust Spark Joy? And the title outshines the thesis in her opinion, but I think the jury's out on that. Let's see. She used to do embedded Rust, and she made training materials for ESP32 and ARM boards, which I'm interested in. I think I'm gonna take a look after this. And previously at Ferris Systems, and here, I'll give the time to her.
Hi, everyone. So, quick show of hands, who has been there for Jean's talk? Okay, good. So she told a lot of interesting things that I don't need to cover. So yeah, hi again, everyone. So in the last few years, I worked on the Ferosine compiler. It's a compiler that can be used in cars, in avionics, in medical equipment, and in planes. So it's safety critical. It's the 4th time I'm giving this talk, but I had to rewrite it completely because, yeah, this is the mecca of the Rust fans. So, yeah, so I hope you like it. And when I rewrote it, I focused more on the actual pains of rewriting the compiler and less on the how cool is Rust. So the art is made by me. So it looks like it has been made by AI and Satan. So that's a good way to remember my name. You just need to remove the N at compile time, and it's Aisata. That will be me. There will be, 3 parts of this talk. So the context, what is safety critical, and the compiler qualification. There is a really good talk by Emilie Albini about that. So I'm just going to cover the basics because part 2 and 3 are a lot about complaining. So before complaining, I need to set up the scene. So yes, second part is how we work to stay close to upstream, because it's a fork, but not a fork, not really, we get to that. And 3 are the known problems, so compiler bugs. And yeah, part 4 is just buy and references. Yes, so, okay, to my shame, I do have a lot of slides at home. I have a lot of marketing-ish slides at home, and I do have 70% of the memory bugs. 70% of serious bugs that come from memory safety. I have undefined behavior and demons flying out of your nose. I have those talks. I have one for C people to convince them, like things that I found on LOLkedin, people that believe their C code is perfect. I have this slide for C++ people where they do recommend themselves to stop using C++ for new project. But this is not going to be about a marketing talk. But the questions I have are often, is it just Rust C that you are doing? And why should I buy your compiler? Like, sell me your compiler. And yeah, I found these questions quite interesting. So, is it just Rust C? Yes, if everything goes well, and this is incredibly hard to make it just Rust C. So it's just Rust C and a part of libcore. It takes a lot of efforts, and I want to share it with you. And then it's not my compiler, right? This is our compiler. This is what open source means. And in safety critical, there's no I should buy a compiler. It's either you must buy it or you must not buy it. And if you must buy it, you need to read the docs. So this is the only request that this is the only thing that is imposed on you if you do safety criticals. So again, I will refer to this talk by Emilie. So the basis of safety critical is that you cannot put whatever code inside of your car or medical equipment or plane. That's you want to live, right? So this is heavily controlled, and this is the only place of software that is heavily controlled. You can't just put whatever. So you can either look at your assembly code and examine it line by line and make sure that it's correct, or you can use qualified tools. So this is the way we are going. So Ferosine today is qualified. We follow those standards, ISO, ISC. According to Emily, they are not boring because they are not telling you what to do or how to do it. Yeah, they're telling you what to achieve, and then you are supposed to find good ways. And yeah, today we are qualified for automotive, industrial, and medical field. And in the end, we send a report to TÜV. It's a German organization that do certification. I will not try to pronounce it again. I always fail. And it has been there since the 1800s. And my colleague Jean told me that at the end, when they're happy with you, they put a factory stamp, like in 1866. True story. So yeah, so how to qualify a compiler? So we first think about the use case of the compiler. So what does it do? It installs, it builds libraries, it builds executable, and it cross-compile, which is very important for us who love embedded. Then we sit down and we look at we do a impact versus detection matrix. So we look at all the ways the compiler can fail, the impact of that bug versus the possibility for detection of that bug. So the lower the detection and the higher impact, the more serious is the bug. Then, compiler deal with languages. So we wrote the Ferosine language specification, and Jean told you that those were donated to the Rust project. That's a way to contribute back. And we do. Then we go through all the tests of the compiler that are already existing, and then we annotate them for all the specification paragraph. So basically, we have specifications, and we must make sure that the behavior of the compiler is in line with those specifications. So, and yeah, there's the famous factory stamp that we're going for. So that's like today the job of my colleague Anna, but we are training other people to do it. So basically, she's sitting with tens of thousands of lines of code, and she's looking at the differences and making sure that she needs to pick up which one are significant for the assessor and which one are not, and make a report on that. And no question must be left unanswered, and even better, the assessor should have no questions at all. It's a very difficult job. So. I'm almost done with this part. So what's the Ferosine compiler? It's a black box that covers the whole compiler. It means that the qualification is end-to-end, like Rust front-end, LLVM back-end, and the linker. So LLVM is a part of this. It's qualified as a black box, so there is a long answer to why LLVM is not qualified as itself, and there is a short answer. It's more practical, so it's more practical like that. Then we really do believe in open source. So what is done? I mean, of course, there are customers, and sometimes they have their needs, and we need to fix as soon as possible. But the spirit is to, when there is something to improve or a bug to fix, we do it upstream, and then we pull it down back to the Ferosine compiler. And so, yeah, technically, it's not a fork. It is a fork, but not a fork, because every two release of Rust-C, there is a release of Ferosine. So a lot of stress, but it's worth. So we really fight to be as current as possible. I think my colleague is in the room, so he's in charge of that, and this is funny. So I'll get to that. So yeah, and then there is this LibCore certified subset. So LibCore is a bit different to certify than the compiler, because for the compiler, Yeah, you saw Jean with the 100% coverage. Yeah. So for a tool, we need just to describe its behavior. We have the specs, and we need to prove that the specs are true. But for the compiler is going to compile the code that is going to run on your machine, but libcore is going to be on your machine. So the code coverage must be 100%. So what she told you before. And despite not being able to trust our tools, this is still something that is compulsory. So there are several levels. There is in code coverage, there is function coverage, line statement coverage, and branch coverage. And for libcore, we need to, and MCDC, yeah. And for libcore, we are aiming for 100% coverage. So that's the difference. So yes. Okay. Congratulations, you made it to the complaining part of this talk. So now that we put the scene. So every morning at between 5 and 5:30, we put in all the changes of the Rust compiler. So it's about 100 to 120 PRs, yeah, roughly, depending how well you work. So question. What do you think it is? Who thinks it is A? It's trivial. Nobody. It's a trick question, come on. Oh, there is one person who thinks it's trivial. Okay, so then everybody else thinks it's going to make you cry. Yeah, okay. So trick question. It's both. So this is my alternative title for this slide, up to date to upstream, and it's fine. It's going so well all the time. So so we have all those tests, right? We have hundreds of tests, and we're making annotations to them. And what does GitHub do? It complains, obviously, when there is like one light change. So sometimes it's extremely, extremely trivial, and an animal can do it, a very smart animal. Like, shout out to my colleague Ada, who just joined. So Mer Giraffe could do that better and faster. Sometimes it's incredibly trivial, and we spend, a lot of time fixing that. And then there is the it depends part. Yeah, so what can happen? LLVM can be broken. So it happens quite often in the form of a linker error. And yeah, the problem is that it's happening after 30 minutes of compiling. So this is painful. We have our own version of LLVM, and we need to, we have our crimes that we're not going to talk about right now. Then, when Rust modify a core subset, somebody talked about, when submodules were moved to subtrees, we have issues with that. I think, oh, great, I mixed up slides. Yeah, sorry, there. And when we're doing those pools, they love conflicts. So this is a graph that my colleague Luca did at the time. So so we do those pools. We do the pool from upstream, we do the pool from subtrees, and we do a pool for libc every day. And I mean, you obviously see immediately what's wrong on this graph. There is so little information and so little arrows. I mean, it's there. It's there, so the first pool can fail, and it happens often. And then you see that if you follow those white lines, they touch the same cargo log files. So we end up with dirty cargo log files, and then we have the subtree pool that is going to also touch the same cargo log files, and the libc pool that we have for some embedded targets. So we end up in a pretty disastrous state, kind of often. Then what also can go wrong? That's after fearing for our lives, we got dev pods. I call them space pods. Okay, I should have updated that. And so those are, I mean, just much faster machines. And and Jean found a recursive bug in that. And just a shout out that soon there is going to be a blog article about that. But we managed to kill some dev pods in the process. So and then we have the certify libcore subset every time we are pulling changes, and we should not never touch the certify subset, because you know the thing that the assessor gave us, this precious factory stamp. If we make changes into the certify subset of libcore, then this is invalidated. So we must protect this subset with our lives, if necessary. So we must be very vigilant with that. Then, yeah, we are trying to contribute back. So when there is any fix to do, we always try to do it upstream. So I have an example for that. What happened when we arrived to Rust 185? Does anyone remember what happened? Okay, I will pretend you replied 185. Stabilized edition 2024, and when edition 2024 was stabilized, then we realized that we were not testing for all editions. So we had 3 choices, like force customer to move, support both versions, and of course do nothing. That's more practical. So we implemented some flags to test for different editions and test for ranges of editions, and my colleagues are at the moment annotating, working on hundreds of tests to contribute back to upstream. So yes, congratulations. So now even more whining. So this is what I learned on Rust while working on that. So I worked on the tooling around the Rust compiler bugs, and I worked on understanding and documenting as well those bugs. And I really, there are some things that I would have preferred to be left in the dark about, but it didn't happen. So it is not a secret catalog. It is, we just track upstream UBs, because there are some UBs that completely defeat the guarantees of the compiler. And since we remember this read the docs thing, this is something that we must document. We must inform all programs have bugs, and we just must know about and inform our customers about that and offer mitigation when possible. So this is taken directly from the Rust website. So rich time system, ownership, memory safety, thread safety. So that's the expectations, and reality is, very difficult. Just embrace the struggle. Right. So this is where this slide comes up. So the compiler has many bugs. We must understand them. We must document them. We must propose a way to detect them. We must mitigate those. So, and this part of the talk is dedicated to the people in here and in other places of the building that are breaking the compiler in all the way possible, and and letting us work on it. So this is how the tooling looks like. So you see it's the version of the compiler on the left, the descriptions of the problem on the right, and then we document when they were introduced, when they were solved, and then we reproduce them, propose the most easy reproduction of possible for a clear explanation, and then mitigation. So here. Whoops, sorry. So this is one that defeats spatial memory safety. So the issue is about Stack Overflow failing at the page boundary on some targets. So a large stack frame can move the stack pointer across multiple pages. And apparently, historically, Rust relied on LLVM for overflow checking. And the idea is to replace that with proper stack probes. But this is not implemented for all targets yet. So when there is no stack probe support, that movement can happen in one jump, so the generated code skipped that page. And it was not faulting, it was just continuing. So this is one of the, So this is one of the issue. This is not. This is we are implementing on the target on which it is missing, and we documented that. It's not too hard to understand. It is just happening. Then I have another example. Rep pact that is rep pact that is producing a dangling reference. So you see that the foo is packed. The packed field might be unaligned, and B is dropped at the end of the scope there. But then when V is dropped, it has a reference. It ends up having a reference to B, and MIRI detects UB. And according to the Rust reference, references to unaligned fields are not allowed because it's undefined behavior. So we do have that. We do have that in the compiler. I have a question to the audience about MIRI, but we'll take it after. And then we have unsafe. So that's a good time to say, because now no mangle doesn't exist like that. I think we need to have unsafe, but since we support old versions of the compiler, since there are 6 versions out there, we need to support old versions, and some problems apply to some versions, so we can just use the last one. So we have this one. So we have a data race of function. So this is about symbol collision at link time. So 2 different crates can both export a no-mangle function with the same symbol name. And on some platform, it is undefined which one the linker is going to resolve to. So what do you think it's going to be? Is it going to print BB, BC, CC, CB? Who do you think this is going to print what you expect, BC? Nobody. Okay, one person. Okay, it actually can happen. It depends. It depends on your machine. So it can be, usually the first one is linked first, usually is BB, but depending on your machine, you can have BC. So this is, that's a little no-mangle issue. It's okay, right? It's the only one, but not really. There are many, everything that is extern C is dangerous. So we need to just be aware of that and tell people. Then I have this one that I really like, the space eating problem. So there are some people in that room or out there that are assigning more than the address space in a variable. Who does that? Somebody here does that. So allocating value on the stack where the total size of value is bigger than the address space will cause the total size to wrap around, so the compiler is not going to fail. And the workaround, do not do that. Yeah, sometimes the workaround are extremely simple. Like you just know that it can happen. Do not do that. And the compiler, the problem is that the compiler silently wraps around and doesn't give an error. And this is really not something that we want. And I would like to conclude by this quote by Jubilee. So first she describes a very unlikely sequence of events where people allocate too much space. But still, if a Rust program expresses a desire to go to a hell of its own making, we are honor bound to send it there. And this is the spirit for us as well. So I think this is all I had today. I spoke faster than I planned, so this is my best picture. And thanks to my colleague that I put some of your names here. Your discussing with you has helped me a lot. Thank you to the organizers who did a lot of very nice things for me. And those are the talk I was talking about and the public docs of Ferosine. Thank you so much.
All right. We'll open the floor to take a question or two.
Hi, so I have a stupid question. So, if Ferosine has a more the safety and Is it ever considered that Ferosine becomes a upstream compiler than Rust-C?
I'm sorry, I didn't get the question. Is it?
Yes. So there's a Ferosine compiler and the Rust-C compiler, and Rust-C is the upstream compiler.
Yes, I mean, if everything goes right, it's the upstream compiler, and yeah, every 12 weeks there is a Ferosine compiler that is close to that is following the Rust-C release, and it's very important because we want to bring in the modernity and all the bug fixes to the Ferosine compiler. So because the alternative is, we know the alternative in safety critical. So so yes, when it works, it is the same with additional targets.
But it's the same. But like, if the Ferosine gives more safety, then why do we need two compilers? And can we use can you all use Ferosine?
Okay, I realized that I didn't. Yes, it is open source. I should have I should have said thank you. You are Kagami.
Yes.
Yeah, Kagami-san. Thank you for reminding me. Yes, it's an open source compiler, and you can go to the GitHub for it, and you can. Yes. Thank you.
So I guess part of what I understand about safety certified software is assessor bodies were against open source for the longest time because, like you said, when you get that stamp, it's not supposed to change. And you did mention that there is a subset that is not supposed to be touched or changed. But what I'm wondering about, how does it work for the parts that do change?
So there is, every time parts move and do change, and this subset also expand. I mean, yeah, there is a long reply, but it's more practical. So when we do change, we have so every time that there is a new release, so my colleague is going to compare, and my colleagues are going to compare all the changes, and let the assessor know what is important, what they should specially pay attention to. And the new changes that are included are going to be revised by the assessor at that point. And the assessor checks the changes of the compiler, but it also checks the processes of the company. So because when you do quality, you can't add it at the end and control at the end.
So does that mean that you're recertifying the compiler every time?
Yeah, every 4 times a year.
Okay.
Yeah, that's Omar.
Yes.
Yes. Okay. I have such a blinding light in my face.
We got time for one more. Oh, there we go.
Hello, thank you for the talk. If I wanted to certify my crate, would I need to use only the subset you have and then do all the documentation and testing on it?
If you want to, okay, that's going to be the marketing part. If you want to certify your crate, then you need to contact us. And yeah, and I mean, we have already a lot of, because I didn't say it in that talk because I was afraid I would be out of time, but we have a lot of targets that are not supported, that we pre-certified, so there is a lot of material already. So you just need to contact us and.
Okay, thank you.
Cool, thank you very much.
Thank you, everyone.
All right, just a bit of housekeeping here before we finish. We are now in the final phase of the track in the conference. We're going to be having drinks available until the end of 7 o'clock. So, sorry, I should be more clear. Drinks are available until 7 o'clock. Sorry, so start of 7. This room specifically needs to be cleared by 6 o'clock. So you guys have got about 20 minutes. Please don't leave things in here or we're going to close the doors, and I'm sure you don't want that. And after that, we'll see you all tomorrow. Venue opens at 8:30 in the morning. Thank you.